Okay, super. Where are we? Yeah. Okay, so now we'll start, but this is little math, so we'll learn math but easy way. Okay, don't worry, we'll go with easy way. This is from the lecture 2.2, and if you do this our session also, then you don't need to see the video and you don't need to bother about what is happening. But it's better, I will suggest to go with the videos also, but you just also check our sessions first. Okay. Okay. Yeah, let's, it's like, okay, no worry, thanks for that. But yeah, we'll learn together also, not a issue. Okay, so what we now understood, like PCA has the issue number one where D is greater than N. That's the main issue, because when D is greater than N, we are having issue in the eigenvalue and eigenvector calculation, which is taking lots of time, which is not acceptable. So we have to find out some solution. So what is happening? What is D here? D is your features, like what you mentioned now: height, height, weight, or whatever may be color, or whatever may be your house location, and anything. Okay, N is nothing but number of samples or number of data points. Okay, N is nothing but number of data points. Just understand it. Okay, and then we know that how we can say X. What is this X? Because we are using this X. Calculate capital X is nothing but, as I mentioned, these are the x1, x2, dash xn. Okay, we are actually doing week 2, and we are calculating week 2.2 session we are doing, because earlier sessions we have already finished 2.1, and now this is important point for the kernel PCA. Okay, so we'll go with that. Okay, and what happened, like we know that X is something we consider, capital X is, this is small x. Okay, this small x1, x2, xn. Okay, what is small x1, x2, xn? That what we just, for example, we consider this is the height, and this is weight, and this is something, these kind of parameters. Okay, x are the small parameter. Okay, and this, what is this? How much is the size of X? It's a D cross n. Like you are having D dimensions and n rows. Okay, so this is what we, the size of X. So I will just write also X belongs to R of D cross n. Okay, and we know that we, what we normally, yeah, normally n is generally greater than D. Okay, like not too much, but n is something greater than D, then you can use our week 1 sessions, like calculate PCA with normal, like I showed you one demo where I'm just drawing the lines without any like any good data, like maybe you remembered in the last week, I think the earlier week, not last week, but last two before week, and I shared you the workshop file also, where it just drawing the line something like this, like this, and like this. So there are some data sets. So here this is something where n is greater than D, so you can normally use the PCA whatever happen. But in case of D is greater than n, okay, this is something happen in this kind of image data set, like when there is an image photo of a person and all, that time this income. Yes. Yes, number of input images will be less. So this is like, maybe I gave you one scenario, maybe there are different scenarios, we are just coming across because our week sir has given this scenario, so I am just explaining about that scenario. But there may be another scenarios also where you know that there is a D dimension is greater than the number of input sample. Okay, so we know that, now we understood that X is nothing but, this is the capital matrix X, where we are just putting all the data in this kind of a matrix. Okay, and we also know, like C is equal to, that covariance matrix is equal to 1 over n summation of I equal to 1 to n xi into xi transpose. Okay, this is what we know, we, because this is from day one we are like going behind this point. Okay, so okay, this is like a covariance matrix. Okay, covariance matrix xi into xi transpose. So okay, and this xi I will write a small xi so you will understand, because this is like a small, this feature xi means this feature, height, weight, and these features. Okay, xi into xi transpose. Okay, this is covariance matrix. And if you do something like, now here if I do this x into x transpose is equal to, what happen, what is x? X is nothing but these values, x1, x2, so on till xn. Okay, which is actually d cross n into, what is this, x transpose, this is something x1, x2, okay, xn, because this is, I'm not going fast, so because I need to connect you to what we are doing like it. Okay, so okay, okay, so this is, yeah, and if you actually solve it now, if you actually solve it, this will come, because x1, x2, and if I just put, yeah, yeah, that's true. So it is d cross d matrix, but that is something which we get because you know that this is, for example, here a b c d. Okay, and this is what a b c d, because this is transpose. For example, this is x and this is x transpose. Okay, so what happened, you are doing this a multiplication, if I want to do is something a square plus b square, like this multiplication, this multiplication, correct? And now what happened, next one, AC in plus BD. I'm just doing matrix multiplication. Okay, AC plus BD, and then C square plus D square. Okay, so this is what exactly, if you actually do the summation of, like if you see the xi into xi transpose, if you do, and if you see that this is summation, this is summation, and if you actually calculate the summation over xi into xi transpose, that's come like the same way what we have like here. So this result xi and this xi transpose is nothing but summation of I equal to 1 to n x small xi into xi transpose. Okay, this is how you will get that. This from here, this is like, you can like maybe take the example and prove it later on, but this is the way. If you do it, then you will get xi into xi transpose. Okay, so that's why what I have written, like earlier we have written c equal to 1 over n. This is what we have written here, c equal to 1 over n x summation of xi transpose, xi into xi transpose. Instead of that, I can write this is also 1 over n capital X, because capital X is now just replaced, because I am just here, if I do this calculation, I will get the xi into xi transpose. So I am just doing x into x transpose. Okay, this is capital. Okay, capital X is nothing but this value. Okay, this value, capital X, which has internally this x1, x2, x3, all the features. So instead of representing the x summation of xi into xi transpose, and now I am saying this is 1 over n x into x transpose. Okay, so we just found that this is what we get it from here. Okay, this is the important point. Okay, and what generally we do in the PCA, like now the main, okay, so here if I actually just replace, like if we now, for example, here c is equal to 1 over n x into x transpose dimension. Okay, maybe I'll just use small font so I can properly write here. So if you actually do this calculation, see x into x transpose, I just now here I mentioned the small example here, a b c d. Consider this is your capital X. Okay, capital X. Okay, this x is here, a b c d, and I'm just transposing it, this one a b c d. What a b c d is there? So see, this is x1, which is a b, x2, whatever I have written, this is c d. Okay, so this is a b c d and this transpose here, and if I do this calculation, a x into x transpose, okay, what x is nothing but this a b c d. Okay, if I do the calculation, it comes like a square b square, a square plus b square, and here ac bd, and c square plus d square. And here in this case, if you actually see what is this, you are doing the summation of, what you are doing, you are just multiplying this, factor with here, means what you are doing, xi here, xi into, so if I consider this one as a one parameter, okay, a as 1 and xi into, you are doing this xi. Yeah, yeah, yes, for example, Murli is here. Yeah, so Murli's height is considered 170. Here Ashwin's height is considered 171, and maybe somebody X person's height is 162. Okay, these are the X. Okay, this is height and this is weight. What about Murli's weight? Consider it is 81. Ashwin's weight is considered 85, and maybe X person's weight is 71. Okay, so these are the height, weight. And how, if I want to put this one here 170, if I just take these two matrices as of now, okay, 170 81, 171 85. Okay, so this is, for example, I just took one X matrix. If I do X transpose of this one, how much it comes? 170, because these rows become column now here. Okay, 171 become 85. And if I actually do X into X transpose, what I am actually doing, this multiply by X into, if I just like this multiplication, 170 into 170 plus 81 into this 81. Correct? Correct. So here just X into X transpose, what it does is 170 into 170 plus 81 into 81. Just see that summation. Okay, next point, what happened here, I'll just type here 170 81 171 85. Okay, so what is happening now? We are doing the multiplication. This is just matrix multiplication. Okay, we are not doing anything else. We have 170 into 171 plus 81 into 85. Okay, the same way here, 171 into 170 plus 85 into 81. Okay, next is 171 square, like instead of 171 into 171 plus 85 into 85. So what you are doing actually here, you are actually doing the same calculation here. What we do in this case, summation of I will do n xi into xi transpose. If I do actually this calculation, this whatever the xi we are having, so x is equal to, if you see, xi means x1 x2 x2 and x3, here x3, and this is x4, this is, and if you do actually this calculation, it gives me the same way 171 here, this value. If I actually do like this calculation, it indirectly gives me this result, same result, x into x transpose. If I do this one, first value of xi into x transpose, first value here, x1 x2 is transpose, x3 x4. What is happening? xi into x transpose, this is the xi of x transpose, this value, correct, first value, because I is starting from 1. What is here? x1 and x1 of transpose x, correct. Next time what happened? x2 of transpose, and then x3 of transpose, x4 of transpose, plus. So like this, if your matrix is very big, so what happened? x5 of transpose, and so on, and then xn of transpose, like this. And if you are doing this kind of math, it's all showing in this math, so that is nothing but you are doing this x into x transpose, same, because x into x transpose you are doing the same, 171 181 171 here. So this matrix, yes, yes, it's just kind of it's like a normal matrix multiplication, but instead of showing that, I am every time, like, instead of writing this value is nothing but 1 to n xi into xi transpose. Instead of writing the summation symbol and then multiplication of or the product of xi into xi transpose, instead of doing this complete calculation, what I am doing, I am just saying it is x into x transpose. For easing or showing that all the calculations, next calculation, it is easy to me show me that x into x transpose, this capital X into x transpose for this term. Instead of saying that it's summation of I equal to 1 to n xi into xi transpose, instead of saying that, I am just writing now x into x transpose. Okay, so capital X into x transpose. So this is the reason I am using x into x transpose. But it is not something because mandatory, but if you do it, then it's very easy for writing. Like if I'm just deriving some mathematical because you know that there are sometimes we what we do, we say let's the value is x, we consider the, for example, in any math, what we say, let's the height is equal to x, because we don't want to say like let's height is equal to 3000 say 6000 5682, let, we don't say like this. So we say let's take some height is equal to x, but then we calculate something like some equation, and then x square is equal to some equation. So it's easy to put the x square and this kind of yes, yes. So it's easy to substitute this big value or any kind of a relation value. You can just put x value, and then you find out the solution of x, and then you consider x is equal to that value, and like some t plus 0.5. This is a some equation. You don't want to put this equation, instead of that you put x. So like this. So instead of writing I is equal to 1 to n xi into xi transpose, I am writing is x into x transpose. That's all. And these are same as we just now we solve this one here. We found that this is what xi transpose into xi transpose summation is nothing but x into x transpose. What is this? Is capital X, and what is this capital X? This is nothing but your same x x2 so on till xn. This is same. Okay, this is the same, and these xi are like here, these xi, this xi, these xi values, these are from here. So just see that this is just we are, yeah, this is just we are considering this c equal to, instead of like now, so instead of saying c is equal to 1 over 1 upon n xi into n to n xi into xi transpose, instead of saying that, what we are saying to this same value 1 over n capital X into, yes, yes, yeah. Without this summation we are saying this is x into x transpose. That's all. Okay, this is what the starting point. Okay, now you know that what we generally do in the PCA calculation, we do that covariance matrix calculation, and we calculate the eigenvalue, eigenvector and all, correct? But what is that eigenvalue vector? What is this eigenvalue and eigenvector calculation? Our main aim is whatever the points are here in the space, we have to figure out some relation into that point and draw some kind of a line which will represent this kind of a point. So we thought, okay, better to draw this way, because, and then we just put all the proxies or projections on this line. Okay, and we found that this is the best line we can achieve with this to represent these points. There is some linear relationship between that point. So we thought that, okay, let's achieve some kind of optimization. So once you get this line, means once you find the w, the direction, okay, once you find the w, so that w will give you some kind of line L. Okay, that best fit line you will get, and you are very much happy. Now you can just represent this complete data set with using representative and the coefficients, and then you can achieve some kind of a compression also in PCA. Okay, in PCA compression. Okay, this is what our main aim in the PCA, represent all these points which are in the space on a line. Okay, and you will get, you can finally represent this as a representative or the coefficient, and then you can achieve the compression that we have seen last time, that all the examples. Okay, so we need to find out the best fit line. So best fit line, what you, yeah, yeah. So see the non-linear, this is the issue number 2. that issue number 2 will come afterwards. Now we are dealing with issue 1. Okay, so issue 2 is if the points are non-linear, something like this, like circle. Okay, so these circles means then this is issue number 2. We'll come to that point also after, at the end of this class we'll also go. Now we are dealing with issue 1 where we need to find out the covariance matrix calculation. Okay, covariance matrix calculation, instead of d cube we want to do with the n cube. Okay, so how we can do with n cube, and this solution will help into the issue number 2 of your non-linear features also. Okay, if the features are having non-linear kind of relationship, so solving that non-linear features also you need to use issue number 1 solution. And now we are checking what is the solution of issue 1. Okay, so this is what we are doing here. Okay, so we are finally need some kind of a w, that is eigenvectors, or the w which gives the maximum variance. Like I know that this side is the giving the maximum variance, so I need this w instead of the other w. So this is our best line which we get. Okay, so you know that we like this is what the best line we get, and this is what the w. So what we need to do is, what is the w, or how to calculate w, like eigenvector. How to get eigenvector? From covariance matrix. Okay, what is covariance matrix? D cross D. Oh, then it's when d is greater than n, that is dangerous. Don't go with the d cube, don't go with the d cube, go with some other n cube. Yes, 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 yes. So you don't go with the d cube, go with n cube, but you simply can't go with n cube. So how we can go with n cube? That is the algorithm we will learn now here. Okay, so we understood now the w is the main thing. And yes, normal. No, no, if n is more, see, generally whatever is the covariance matrix you calculate na, it is d cross d. And if n is already more, then you don't need to bother. Anyway you are calculating d cross d, so you are not going with any n calculation here. Your earlier PCA algorithm, whatever you learn, yeah, that is by default. By default, okay, by default PCA has time complexity and the covariance calculation, and this time complexity is d cube. So if d is anyway less, in this case d is anyway less, no worry, you can happily go. But when your d is too much greater than n, that time d cube is dangerous. You cannot go with this much d cube calculation. Okay, so you need to have solution with n cube, and that n cube we are now checking that. Okay, so we understood now. Here we want to find out the w. Okay, this is the aim of the PCA. Okay, but now what is the solution? So we are now finding this math. Okay, we are starting the mathematical calculation now. Okay, so we know that eigen values, whatever the eigen value or whatever the eigen equation, we know that av equal to lambda v, that is our famous eigen equation. Correct, eigen equation, because we have gone through earlier courses, we know that av equal to lambda v. So how we can write here? A is what? Some covariance matrix. In our case, what is it? Is C. Correct, C. Okay, v is what? Eigenvector, but we write this one as a wk, because we know that. Correct. So wk, why I am taking the k is like how many iterations we need to do, so I am just writing wk here. Okay, and what is lambda? That is same eigenvalue. What is that? V is also same wk, that is the best, our famous eigen equation. Okay, this is the equation, eigen equation. Okay, so what I am doing now, I am just replacing now each part. Okay, well, you know that what is C, because we just now say C is equal to 1 over n x into x transpose. Correct, we just figure out this equation in the earlier. Okay, this here. So yeah, So you just need to understand it, because sometime what happen if you go to any kind of R&D work and also they will ask you like, can you derive this one? So you should know that thing better. Okay, so we are just now putting these things. C is what here, this for example, this is equation 1, this is you are having equation 2 for example. So I am putting now 2 into this one equation, 1 over n x into x transpose, okay, wk as it is lambda wk. Okay, I hope you are now with me. Okay, next point, I'm just rearranging this equation because this is what sir has given, but you will like say, oh, what is what, if you just miss this track then you will not understand what he is doing. So better I'm just giving you, I'm just rearranging this lambda, I'm just bringing back here, wk equal to 1 over n, these values I'm just writing here, 1 over n x into x transpose divided by this n is already here, okay, and this lambda is here. So this is x into x transpose divided by n lambda, which is nothing but this wk, this wk, okay, this wk is here, wk, okay, wk is equal to x into x transpose divided by n lambda. So what happened now here, so what we do, so we know that what is x, this x, because we have already, we already got that x into x transpose, this equation, what we consider this 1 over n I equal to 1 to n xi into xi transpose, correct. This equation can also be written like this, correct. You got that, because it is like, yeah, so it is something we are just here only, we are not. Hmm. Yes. Because you are not doing all the W calculation 1, 2, 3, 4, 5, 6, 7, 8, 9. So as of now, I am just saying that I am just going till iterations k iterations only. I am not going till all the iterations. So I am interested in only that WK. Yes. We are going only that equations. Okay. So x into x transpose of n, these value, these things. Okay, how we can do, how we can write this is equal to 1 over n, same as it is nothing but I equal to 1 to n xi into xi transpose, and this n divided by this lambda is as it is, this lambda. Okay, this is as it is, you are not doing anything else, you are just simply now see, this is important, I don't want to like go in the next step immediately. So is 1 over n, so I'm just putting xi into, so I think I just uh, okay, here this point I just yes, oh okay, I actually, okay, this w I just here, this w, oh this w I just miss this wk here, this w I miss this one, wk I'm just putting here. Okay, so this is nothing but into wk, this wk I missed here, so I'm just putting wk here, and this is nothing but wk here, and this final, this equal to, if I just replace, oh sorry, xi into xi transpose, this lambda I am taking inside because anyway it's not outside, so you can take inside, into this wk was earlier here, this wk. Okay, so this is what you need to calculate, this is the what you are interested in, you are finally interested in the eigenvector, correct. This is the eigenvector you want to calculate, but what is the problem here, you found that if you want to calculate wk, if you want to calculate this wk, okay, what is this, it is actually, see, this is some type of a constant, this is xi into xi transpose divided by n lambda is some constant time wk, means what, this want to calculate this wk, you are just multiplying or scaling the wk with some value, some constant, you are just scaling this like 5 into wk or 6 into wk or 7 into wk, what you are doing, you are just scaling, you are multiplying with the wk and doing like this cwk, like this way. Okay, 5 6 7. So you are just shifting that here. This is earlier wk, this is next wk. No, I will come, that's what, that's the main thing now I want to say you. So wk here, that's correct observation you did, that is what, that is the point here. So wk is the linear combination is linear combination of data points. Okay, what is the linear combination means, this what, c into wk, what is that, this is linear combination, y equal to mx, linear combination like this. C into wk is a linear combination. So this wk is a linear combination of the data points. Okay, but see this. Okay, but I'm not interested in this wk. So what I am doing, like I'm just rearranging now, I'm just rearranging this now. So xi, this I will take this w xi transpose. Okay, this xi transpose, these two I will now just do like this, xi transpose into wk divided by n lambda, and now this xi I am just taking this out. Okay, this out. So what you can see, to get actual wk, to get actual eigenvector, you are multiplying, you are doing the summation of what, summation of some constant c, this is constant. Okay, this is the constant, this is actually the constant. Okay, I just rearrange the values, xi transpose into wk I took 1 and I put xi outside of this. Okay, these are the constant. So to get the eigenvectors, I am actually doing summation of scaling of these data points, or summation of, or linear combination of the data points. I am just doing the summation of these points to get the wk. See, for example, consider this as a I equal to 1 to n constant or some value into xi. So you are just doing like y equal to summation of some value mx. Okay, c is 0. Okay, I to 0 to n is xi. So yeah, like this. So this is what, this is linear combination, y equal to mx and summation of that. So this is what we are also having here. This is the wk, and your actual question is correct now. Okay, what you said, that what you also mentioned you here, we need what is the difference between this wk and this other wk here. Okay, because in PCA we are interested in the finding the eigenvector, we are interested in finding this wk in PCA, that's fine. But to calculate this wk, you have to get this wk, means this is nothing, it is like to get a you have to calculate a, like you have to use a, but you cannot do, like you cannot calculate wk with this wk because they both are same. So finally it is like whether egg is first or whether chicken is first, is this kind of situation, you don't know, sir. Yes, yes. So you cannot like simply calculate it, like you need to calculate wk by using the wk. This is not at all possible, this is not at all, anyway it's not possible. So what happened, now we have to find out something, but before that what we said, that to this equation, see this whatever these xi, so I'm just taking out this xi outside, xi transpose wk, this equation outside into n lambda, this we consider as alpha. Okay, alpha k. Let's say this equation xi transpose wk divided by n alpha is equal to alpha k. Okay, and what is remaining now, summation of I equal to 1 to n xi. What is this xi? Because we know that this is capital X, correct, because that what we have calculated here earlier. So what is this, in this case wk is equal to capital X into alpha k. This is as of now. Okay, this is, remember this equation. Okay, how we got x is nothing but this value. Okay, like this way, and then alpha k, how we got xi transpose wk is n lambda is, let's say like this is as a alpha k. Okay, this is very much now here onwards is interesting, going on interesting. Okay, this is your equation number 3 4. Yeah, no, both are same only, but we cannot simply, now we cannot simply calculate wk using wk, correct, it's not possible, it's not at all possible. And you said that okay, alpha is equal to xi transpose wk into n lambda. So you are saying we need to calculate the wk, and this depends upon alpha, and alpha is also wk. Means you cannot calculate alpha using the wk, because wk we don't have. So you have to calculate alpha, and you have to calculate some equations which doesn't have the wk included. So you have to figure out the equation of alpha which is excluding, okay, which is excluding your wk. So I need to find out alpha, this equation, but I need to find out this value alpha k value, which does not have wk at all into that. So now we understood that, okay, we need to find out, earlier we need to find out wk, what is nothing but x into alpha k, but alpha k is this value xi into wk, and wk is what we don't know. So you cannot use this equation xi transpose into wk by n lambda, you cannot use n lambda, this equation, to get wk. You know, this is what alpha into, if you just simply multiply your data points, what is x is data point, you need to multiply x with some kind of alpha value to get actual our PCA eigenvectors. That's all our main aim, that's all the picture is about. 3 hours movie is about finding wk. This is what we want, and what you want to do, x into alpha k, but alpha k is this xi into wk transpose by n lambda. This is the alpha k, and that is not possible, that is not allowed here, because he is saying that it's allowed to calculate the alpha, I am happy, but you don't use this xi transpose wk divided by n lambda equation. You use other whatever equation you want, you can derive new equation, but don't use this xi into wk upon n lambda, this equation. Okay, so in this case what happened now, here what happened, alpha, yes, alpha k has some meaning, I'll tell, alpha k has some meaning. It is the eigenvector, it is actually an eigenvector, because see what we know, I don't know, you know, I'm just trying to write, but okay, I'm just trying to write with my thing. Okay, now it's running. Okay, so what we know, earlier we found that c into lambda k equal to c into wk equal to, I will just, this is not the correct one, c into the wk into lambda into wk. This is what we have equation, earlier equation. Okay, before any kind of issues in the PCA, we know this equation, we have this covariance matrix wk. Okay, but this wk is the eigenvector of this equation, correct, c into wk into lambda k, this is the eigenvector of this equation. But there will be some another equation where alpha will be the eigenvector of that equation. Suppose x, and then this is some value, and this is alpha. Okay, so this will be the eigenvector of some equation, and that equation we are deriving now. So this is the equation you are deriving now, and this alpha k is nothing but the eigenvector, and this, now we will go next step. Okay, so you found that, so you understood what is alpha k here, it is eigenvector, but we are now going to that step. So alpha k is some kind of eigenvector of some equation that we are deriving now. So what happened, like I just give you the what was the final climax of the movie but actually I will come to that point, but I just mentioned you this alpha k is some kind of eigenvector of some equation, and that equation we need to derive. And once you get that alpha k, what you do, once you get the alpha k, what you do, you just multiply with x to get w, that's all. So you got eigenvectors, and that's all. Then you draw the line, and you say, okay, drop all the points on this line, and you can like finish your PCA, that's all. You get w, that's all. But alpha, what is that alpha? That is something you are calculating. And how to calculate? He said earlier, he said xi transpose into wk upon n lambda you use, but I am calculating wk. Why I don't have wk, so I cannot use this equation. Okay, you can't use this equation, then you have to find out some other equation of alpha and get the alpha, and then multiply with your x and get w. Okay, so that is what our now voyage. Now this is our voyage to calculate the alpha. So we have to try to find out alpha k value. Okay, this alpha k value. So what happened? You know, now you understood that. Okay, wk equal to x capital X into alpha k. That what we have the equation. Okay, and in this one, you know that like, this is like a normal. Like I will once again, because here these two equations are now repeatingly come. Okay, lambda k into wk. This is what we know, that av equal to lambda v eigen values. This eigen equation, you know that. Okay, eigen equation, and that I am writing this way, eigen equation. In our case, cwk is equal to lambda into wk. Now what I am doing, okay, these equations, you understood this equation, correct? X is equal to capital X into alpha k. Okay, now what I am doing, this equation, now I will just once again, what I will do, I will replace this equation one more time. Okay, these steps are already there in the search video, but I am explaining each step more detail, so you will see what's happening. So what is c? C is nothing but 1 over n x into x transpose. Okay, this is c. What is wk? Just now you calculated, x into alpha k is your wk, correct? X into alpha k. Okay, that lambda k is as it is, and the same way this wk, I am just once again writing x into alpha k. I just rearrange, I just put this c equal to what? This is c, this is c, this is w, this is also w. Okay, these are the values of c and w. Okay, here just I am putting, so I am not doing anything else here. So if you rearrange that, like if you just simply rearrange this equation, like n, you will send it this side, x into x transpose. Okay, maybe I will use the same green color, so it is something, so same way. Okay, x into x transpose. Okay, x into alpha k. Just I am writing. Okay, and this n I am sending here, n into lambda k, as it is, or everything is as it is. I am not doing any changes. Okay, this is something what I have done here. Okay, here see, in this one, now, like whenever you are deriving something, na, you are using some kind of your own assumptions into that to make it like go with to that proper solution direction. So it is not something you are following some proper steps 1 2 3 4 5 6. It's not something like you have deriving something. So here in derivations, now what happen, I will multiply with x transpose to both side, multiply x transpose, maybe this is equation number 3, so x transpose to equation number 3. Okay, x into this value, x into x transpose, x into alpha k, nothing happen. Okay, x transpose n lambda k x into alpha k. Okay, this is equation 4. See, this is something, this you know that matrix multiplication is not the commutative, like you cannot simply say like you know that n into d, next matrix has to be d into n or some value. If this and this is same of the matrix, then you can do matrix multiplication, correct? So you cannot simply like put this here, like you cannot make d into n and then this value d into n. You can't do that because these are not same, so they are not like commutative, but they are like associative. Like you can just create the group of each group of these, you can like put this one here. Okay, you can create the group of this. So I am now creating the group of this. Okay, this is one group, now this is one group. Okay, now this n lambda k is as it is. Here I take this x transpose x into alpha. Okay, this is one equation. Now you have seen that there are so many x transpose x transpose x. Okay, let's say we say that we say x transpose x is equal to some k value. Okay, this is the k value here. Okay, let's say this is equal to k value. So what you say, k into which one? skip. No, we cannot divide that, but so what I'm doing here, I'm just multiplying both sides same value. Okay, so for example, yeah, X transpose same. So then you can like remove it also, and you can just add as also. Okay, so here I said that okay, it is like a K into K. See, these are the equations very much important. If I just skip and then I say that this is the final value, then you will say magically it appears. But if you want to understand the algorithm, you just need to know how we are going. Okay, so this is what we say, x into x is equal to x transpose into x is equal to k. So k, we put that k value here in the equation number 6. So we say that k square alpha k equal to n lambda k into k alpha k. Okay, this is seventh equation. Just like I'm just giving equation number here, so you will understand what is that. And you know that, see, we are having issue with d cross d. That is the problem. We are having the issue with d cross d, but now what happened, this is becoming how we got d cross d, that is x into x transpose, that is d cross d. But now see here, we are going towards now n cross n, some way we are now going. When it is d cross d, x into x transpose is d cross d, but if you see this value, it is now n cross n. This x into x transpose, this value is n cross n value. Okay, we are just moving towards that side, we are actually going towards that side. Okay, so we need this alpha k. So here, so this is alpha k. Okay, so now we are going towards n cross n side. Okay, just be there. Okay, so in this case we need to find, here we need this alpha k, okay, which satisfies below equation. What is that below equation? Is nothing but, see, if this is k square, this is k, so I am just now dividing by k just to eliminate this k. So what I am doing, just divided by this k, divided by this k, so I will get next equation as k into alpha k equal to n lambda k into alpha k. Okay, so this is the equation we got. Okay, so we need this alpha k which satisfied below equation, which is this value k into alpha k. So you don't want any alpha k. Okay, but don't consider like, okay, alpha, I just earlier I showed you xi transpose wk divided by n lambda k. You said that okay, I want this alpha k, but this alpha k depends on wk, so you can't take. But what you want, you need some other alpha k which satisfy this equation, k into alpha k equal to n lambda k into alpha k. You need to satisfy this equation. Okay, that's fine. But what is this? So what is this k? K is what? K is x transpose x. This is nothing but your k value. Okay, you can put this k here. So if you do x transpose x into alpha k equal to n lambda k into alpha k, that you need to satisfy. But you will say, okay, but what this equation looks like, I look like, this looks like something like, as I know, like a into v equal to lambda v. That is what the eigen value, eigen equation, we know that a v equal to lambda v. So you can see a k, okay, lambda this here, this lambda is also here, these two here, here k is here, but this lambda is here lambda k, means this is also some kind of eigen equation, correct? This is eigen equation because we just derived now. So when you see this equation, so it's saying that you are having so many alpha k values. Okay, alpha k is 1 2 3 4 5 6 7, like the eigenvector values. Okay, some values are here, and you want to choose that equation which satisfies this k into alpha k equal to n into lambda k alpha k. What is that? X into x transpose x alpha k n into lambda k in alpha k. So you need to find out the alpha k which satisfy this equation. Okay, this equation, this is one point. So that this is one thing which you need to now see, but we are now going to the next point. This is one equation or one need or one basic important thing you need to find out. So alpha k should not be something any alpha k, it has to satisfy this equation or this equation, equation 8 or equation 9 for example. We need to find out alpha k. Alpha k is nothing but some kind of a vector. Alpha k is some kind of, here this way, this value. We earlier we say that because wk is equal to x into alpha k. So for getting wk you need to find out alpha k. So how you get alpha k? Alpha k is nothing but the alpha k has to satisfy this equation. Once it's satisfied, you are having number of alpha k's, you found that this one of the alpha k is satisfying this equation. So you said that yeah, I got alpha k, then you just multiply with your data points, whatever the data matrix you are having, you just multiply it, then you get a wk. That's all, that PCA is done. And so what is that alpha k? So alpha k is now depends upon n cross n matrix instead of d cross d. Okay, but you will say, see Ashwin, this is x is alpha k equal to n into alpha k, it's okay, I am happy, but is it like a unique equation or it is like any kind of equation, like anyone can it's like a generic equation? So if you see this eigen equation, whatever, now equation number 8 what I said you, so for example if I say alpha k is equal to some u vector, okay, so what I will do, k into this alpha k is u vector, k into u equal to n lambda k, okay, into this u, okay, that's fine, okay, that's okay, that's very good. Like you, because this say that the u vector, whatever u vector, it is satisfying 8, this equation 8, u vector is satisfying equation 8, I am saying u is satisfying, okay, that's fantastic. But what about this, k is equal to 2 into u n lambda k, 2 into u, it is actually just this kind of a scaling, this u, then this u, then this u, then this u, but means this is not the unique equation, this is not the unique equation, it is like satisfying with any amount, any type of u scaling, u2, u3, u4, u, or u by 2, or u by 2, or something like minus u by 2, or anything. It is just it is just multiplication of that, scaling that u value. But we don't want something, yeah, yeah, k, no, k is equal to, no, I'm, yeah, yeah, here kx is what, kx into x transpose, okay, this is sorry, x transpose, x, sorry, I just want to, x is x transpose into x, this value. So if you put this value, because these are the same equation what we have, like here what this equation equation number 8, you can see this equation, okay. So you want some alpha k, which satisfy this equation number 8. Alpha k may be any vector, any eigenvector. You may, I just, for example, I use u because in our videos sir has used u, so you should not feel that you heard some different, so that's why I'm using u, okay. If I say I'm having alpha k equal to u, any eigenvectors, then this equation here, okay, k into u. But if I say it is like a, I'm just scaling now, I'm just like how you know that c into w, I'm just scaling now 2u, I say 2u, it's a linear combination, no? So it's a linear, so I'm just saying 2u into u, that also satisfies the same equation, k into alpha k, okay. If I take 3u, it also satisfies equation number 8, this equation, okay, it always satisfies this. But this become like a generic, alpha k is generic, but my alpha k won't, like if it is this much easy, you are just getting u2, u3, u4, u5u, if this much it is easy, then we don't need to bother about like that many mathematical calculation and all. You simply take any u and say that, hey, now my work is done, I am happily doing this calculation. But no, this is not the solution. You don't need, you should not take every u here, you should not take u, u2, u3, u4, u5, u, or minus u by 2, like anything, minus 5u, u, or anything. So what is this in actual equation, in this earlier equation, you know that what here, you know, maybe I will write here the equation one more time. You know that our normal equation, our earlier equation is what, c into wk Okay, lambda k into wk. That is what our earlier equation, eigen equations in normal like a PCA eigen equation. Okay, in that equation. But what is this wk? Wk has unit circle length. Okay, means this wk is length of wk is 1. You want some vector whose unit length, whose length is 1, has a unit length 1. You want some circle area of wk, that area only you are interested. You are not interested in with wk greater than some 3 2u 3u 4, you are not interested. You are just interested in this circle which has that value of square of this the length of this your unit vector should be 1. Okay, so you are interested into that w only, that u only. You are not interested in all the 3u 4u 5u 6u 7u and all these things. Okay, so we need the direction with length equal to 1. Okay, we need the direction when length equal to 1. Means what? Means what? That wk should be equal to 1. How you write wk equal to because this is square you mentioned, that is nothing but wk transpose wk. Because in vector you don't, you should not write wk into wk. This is not the vector multiplication, because this you have to transpose it, so then only it multiplication happen. So you cannot like 2 3 and into 2 3, that's not possible. You have to 2 3 and the next one is like 2 3, something like this, then only you can do the multiplication, or reverse also you can do that. Okay, so you need to write like this. Okay, wk into wk which has a unit length equal to 1. Okay, so this is what we need. We need the direction where the length is equal to 1. You don't need any kind of alpha k or any kind of the eigenvectors of this equation number 8. You should not take any kind of eigenvector of this equation. Okay, the 8 or 9, this equation, this 8 or this 9 equation, you should not take any kind of eigenvector. We want to take the eigenvector which has a unit length equal to 1, which has a direction or which has a length equal to 1. Okay, that is what our main aim. Okay, so in calculating that value, because here now you understood, like till here we need alpha k. Alpha k, why we need alpha k? Okay, why we need alpha k? Yeah, yeah. Okay, yeah. Okay, here. Can I go up on there? Yeah. Okay. So okay, what? Okay, I will tell you. So you understood till here wk is equal to x into alpha k here. Huh? You understood here. Okay. So we'll do it here. Okay. Small one here. So I said that alpha k is what? Alpha k is equal to xi into wk divided by n lambda. And correct, but one, that is what, because you finally in PCA's final aim is wk is equal to x into alpha k. Okay, final aim of PCA is to get eigenvector. So don't bother, like you say that you are the, maybe you are the boss of a company and your employee say, sir, we are doing xyz. So you said, I don't want to hear anything, I want only the eigenvector wk. You calculate whatever may be in different way. The one person said that, sir, x into alpha k you will get wk. You say, very good, I am happy with that equation. I am now, I don't want to now do any kind of changes. I am interested only wk because I am PCA. I want eigenvector, that's all. And I am giving, you mentioned that x into alpha k is the equation. Perfect. But next that same person says, but sir, alpha k is equal to xi into wk divided by n lambda. And then you say, what? Because it is wk, it's not at all accepted. I want to calculate wk and you are using wk, it's not happen, because we don't have wk and you, so it's, this equation is false. Like then I said that, okay, you go and try to find out another equation of alpha k. You try to get another equation of alpha k which doesn't have wk. Okay, which doesn't have wk, you try to find. This guy will, this guy go and then he try to figure out what is the another equation of alpha k. So what we did here, okay, what we did, so maybe quickly I'll just mention because this earlier things. Okay, so we just said that, see, wk equal to x alpha k, this is what we are having. Okay, so what we did, we know that the equation av equal to lambda v, eigen equation. In our case, what is c into wk equal to lambda k into wk. This is our equation. Okay, in our case, this eigen equation. Okay, this is what we are now having, x into alpha k, and we now place c into wk. What we are now having, we have, I write we have, this is what we derived till now. So you need to find out some alpha k which give me this wk. Okay, you need to find out some alpha k which give me this wk, and that is my final aim of the PCA algorithm. Okay, wk, to get the wk. And now for getting that, so you now say that, now just forget about this equation. Okay, just forget about this line. Okay, now you are now deriving, now you are on the voyage to find out the alpha k. So to get the alpha k, we say that we know that cwk is equal to alpha k, this is wk. That is what our eigen equation. That is what our eigen equation. Okay, sorry, I'll use. Okay, that is what our eigen equation. So I replace c by 1 over n x into x transpose, and wk is what? Wk is this equation, x into alpha k. Okay, alpha k as it is, this alpha k is here as it is, and wk is what? Once again is equal to x into alpha k. I just put the same equation. Okay, this wk as it is I put here. Okay, this wk I put as it is here, here as it is. Okay, so I'm just rearranging it, like you take this and like consider this mathematics here, and just put here x into x transpose, x into alpha k equal to n, this n here, lambda k, x into alpha k. This is just a rearrangement of the equation. Okay, this rearranging. Okay, rearranging. Okay, then you said okay, that's fine. Can I just simply now here multiply, this is extra step. Okay, multiply, this is some equation number, maybe what we put this equation number. So this is what the equation number 5. Okay, this is what the equation number 5. So I am just now multiplying x transpose into equation number 5. I am just multiplying now here x transpose, x into x transpose, x alpha k n lambda k x transpose. Just I am just putting now here inside just to have you understand this. Okay, this is now equation number 6 for you. Okay, I am just multiplying x transpose. Okay, this, that's why maybe you lost the earlier things, but now here. Okay, now I just multiplied this x transpose and x transpose. It's not nothing, it's just multiplying both sides. Okay, LHS and RHS. Now in this case I am now rearranging this together, because in the matrix you cannot simply like just do commutative. It's like matrix multiplications are not commutative. It's like you can do associative, like you can just group them together also, that's not a problem, but you cannot change the places, you can group them together. So here what happened, I am just creating one group, x transpose into x, these two, and this x transpose and this x transpose one group, alpha k n lambda k, this x and this x transpose one group, and lambda k, equation 7. Okay, and you said that, let's say, because it looks little bigger, so let's say x transpose x equal to k. So what is this? K into k alpha k and lambda k, k into your alpha k. You got till now here? Yeah, see here, you are not doing any kind of different things. So just here, like k into is what? K square alpha k equal to n lambda k, this k is same alpha k. I am just I can just simply write this like this k and this k cancel, but I just don't want to do. I just thought to go with the next step. So I am now in this step, I am doing k into alpha k, because for dividing both side by k, like if I can say equation 9 by k, I am just doing, okay, doing equation 9 by k. So k into alpha k equal to n lambda k alpha k. This is what your equation 10. So from this equation, we found that maybe there are different eigenvectors, like eigenvector w1, w2, w3, w4, like or consider eigenvector as a u1, u2, u3, u4, u5, u6, u6, any number of eigenvectors. But you don't need any kind of eigenvectors which simply, like, you cannot put any eigenvectors there. So this equation, if you see here, this looks like some kind of, like, we know that our eigenvalue eigenequation AV equal to what is that, lambda V. Can you see this? Correct? Can you see there is a similarity between this equation number 10 and this equation AV lambda with this eigenvalue eigenequation? You can see this A same, this same, and the same V is also going to this, and lambda k, instead of n lambda k, instead of lambda we are having n lambda k. That's okay, the scaling of lambda k. So it looks like a eigenequation. Correct? This looks like some kind of a eigenequation. And let's say this eigenequation, okay, this equation 10, now you are now with us here, you can understand now here. Correct? You got it till equation 10. Correct? Okay. Now what I said that earlier, for example, this, now what happened, this alpha k is what, if it is eigenequation, alpha k is what, alpha k looks like some kind of eigenvector. Correct? But eigenvector of what? Eigenvector of this equation, equation number of 10, of equation 10. Correct? Alpha k is looks like, if this eigenvalue, this equation, eigenequation, if you see this eigenequation here, this and this equation number 10 looks like similar. That's why we thought that, okay, if they are looks like similar, means alpha k is something like eigenvector. Yeah, eigenvector of what? Equation number 10. Means I can take any alpha k. No, you cannot take. But let's see, if you see, one of the eigenvector is u, ku equal to n lambda k into u. Let's say you have eigenvector equal to u. Okay, I'm just showing now this equation. Okay, I'm just telling after this. Okay, what happened? Ku equal to n lambda k into u. Okay, that's fantastic, because you satisfy equation number 10 here. This eigenvector u, here u, that is the eigenvector, satisfies equation 10. You said that's fantastic, that's okay. And you said, okay, next time can I take 2u, because it's just scaling, n into lambda k to u. You are scaling, like you are anyway having one line, this u eigenvector, you are saying, sir, can I take 2u, can I take 3u here, can I take maybe 5u, can I take all the u's? Because this also satisfy equation number 10, because these are the linear equations. Like you can see that this is like just multiplication and just multiplying with n lambda k. This is like satisfying both the equations. Okay, both this u, 2u satisfy equation number 2. They are satisfying equation number equation number 10. They are satisfying equation number 10. But what, you know that, because see, these are related with the alpha k, wk only. All are coming, because wk, you want wk which has x into alpha k, and you don't want to take any alpha k which gives you wk, because you know that wk's length is 1. Correct? Length of wk, because we saw that we are restricting the wk should have unit length. So this wk will be here. You are interested in that wk which has unit length. You don't want any alpha k which gives different wk which will be here, here, or here. No, I just need some wk which gives me unit length here, this wk on the unit circle. I don't want any wk outside the unit circle. I want everything on the unit circle. That's fantastic. You want wk on the unit circle, means this kind of restrictions you are having on wk. So how this, because you are saying x into alpha k give you wk, means there should be some restrictions on alpha k, because alpha k, you need some kind of alpha k which gives you wk which has unit length 1. Don't take any alpha k 2, 3, 4, 5u, 6u, 7u. Don't take like this. Take the alpha k which gives you wk of unit length 1. So what is that alpha k? Now we are trying to find out the another equation. Now we have one equation here. One equation is what? This equation is, we have one equation number 10, x into alpha k equal to n in lambda k alpha k. So this is one equation you have to satisfy. You need the alpha k which has to satisfy this equation, which has to satisfy this equation. That is equation 1 for you. Okay, this equation you have to, any alpha k has to satisfy, but there is another equation which also that alpha k has to satisfy. Then only you choose that alpha k for as a wk, for the wk. So you got it, this alpha k here has to satisfy this equation, but there is one more equation it has to satisfy. Then only you will multiply that alpha k with x and to get wk, that is the eigenvector, and then your PCA is done. So that equation we are now finding out what is that equation, what is the another equation. Okay, that one equation is okay here, but now we need to find out what is another equation, and we are now going toward that point. So what we have now put the restrictions is that I need the wk with the unit length. I need some alpha k which give me this wk, I need the wk of unit length. So don't give me any alpha k which bring me wk with unit length with length equal to more than 1. No, I need some alpha k which give me equal to 1 unit length of wk. So that's equation I am solving. So we know that wk equal to x into alpha k. Okay, we know that this is nothing but here. So what we do, just do, okay, let's do wk transpose into wk. We need to find out what is wk transpose wk, wk transpose into wk. Here we need to find out this one. So what is that? We know the x into alpha k. This is nothing but what? X into alpha k transpose, because this wk is what? X into alpha k. It's transpose, okay, into x into alpha k. Okay, till now here this fine, correct? So what is here? You know that because we already know the wk's unit length is 1, correct? It's of unit length 1. So this is nothing but wk transpose wk equal to here. I'm just taking this alpha k transpose here, and this what this x transpose, this is what, you know that AB transpose is what? B transpose A transpose, correct? This is what we know, that matrix AB transpose is B transpose into A transpose. The same way x into alpha k is what? Alpha k transpose into x transpose, and this earlier this value is as it is, x into this x into alpha k, okay, this value. But we already know this unit length, this is the unit length which is equal to 1. We know that because we need wk length should be 1. How you write anything in a vector? We write generally wk transpose into wk is having unit length 1. So same way here, wk transpose of into wk is you having unit length 1. That's all. You got 1 now. You got 1 for this, and this is what the next, this equation is alpha k transpose x transpose x, because I'm just trying to write here alpha k, and this is what x transpose x is what? We know that here earlier we mentioned this is nothing but k, because in earlier equations k is equal to x, because we don't want to write everything together. We just mentioned this is like a k equation. Here you can see here, okay, this here, okay, k is equal to x transpose into x. So I am just writing now 1 equal to alpha k transpose into k into alpha k. Remember this equation, okay? So we need to find the alpha k here that satisfies first equation. So here we just wrote here this equation, this one, k into alpha k n lambda k into alpha k. So you have already this equation, k into alpha k n lambda k into alpha k. This is equation 1, has to satisfy, and the equation, next equation is alpha k transpose k into alpha k has to be 1. If these two equations, if the given alpha, if you have so many alpha, that is unit length. No, we mentioned na earlier here the unit length of your W in our PCA we every time say na, like W should have unit length, correct? Correct. So how we write WK? WK, see A square, how you write? A into A, correct? Normal A into A, correct? A into A. But in if it is a vector, how you write? Because you cannot do like this into this, correct? You have to transpose it, correct? So that's how we are writing. If it is a vector, if it is a B is a vector, B square, how you write? B transpose into B. B transpose into B. So how you write for WK? WK square, WK transpose into W. And you know that WK square means that unit length equal to 1. That's why we took 1. Got it? Got it here, ma'am? Okay. So now we said that, okay, this gives us the another equation of alpha k that say that, so if some alpha k satisfy this equation, means that alpha k will generate wk of unit length 1. That alpha k generate the wk of, wk means what? That is the eigenvector of unit length 1. So you don't need to now bother about, you don't need to think about, okay, which alpha k should I take which gives me w as unit length 1. Okay, you take one alpha k and check whether that alpha k satisfy this equation or not. Alpha k transpose k into alpha k equal to 1. If this comes, if this given alpha k give you equal to 1 for this operation alpha k transpose k into alpha k, if gives you this equal to 1, then you choose that alpha k. That's all. So once you get this alpha k, what is k? K is what? K is equal to x transpose x. Okay, k is equal to x transpose x. Okay, so you need to now figure out which alpha k I need. The alpha k which need this satisfies. I need the alpha k. I need the alpha k which satisfies these two important equation, which satisfied k into alpha k equal to n lambda k into alpha k and alpha k transpose k into alpha k equal to 1. So I need the alpha k which satisfies these two equation. If that alpha k satisfies the equation, yes, these two alpha k satisfy the equation, then what I will do? I will simply multiply that alpha k with my data points x, okay, then directly I will get eigenvectors. That's all. The PCA want the eigenvectors. Once you get the eigenvectors wk, I will just simply go and see that which is the eigenvector. Okay, this is the eigenvectors here. This is the location. Okay, then put this line through that point. That's all. So this is the best line you got. That is what the PCA want. Best line. Once you get this eigenvector wk, that's all. The PCA want this line only. And for getting that line, you need alpha k. So earlier what happened? We got alpha k as xi transpose wk upon n lambda k, and you said that no, I don't want this, I don't want this alpha k which has multiplication, which has this wk inside, because I need to find a wk and I should not depend upon my alpha k should not depend upon this wk. Means this equation of alpha k is not good. We are saying no, I don't want. Okay, reject it. So then you started doing research and you found that, okay, so I can maybe get the alpha k which satisfy, because I cannot maybe, but I can, like you have derived it with the mathematical equation 1 2 3 4 5 6 and 10. So you derived that equations and you found that you need the alpha k which satisfy k into alpha k. You need the alpha k which satisfied k into alpha k equal to, sorry, I should not write on top this. You need the alpha k which satisfies k into alpha k equal to n lambda k into alpha k, and you need the wk should have unit length 1. That circle should have unit length 1. It should not go outside that. So you are interested in wk with unit length 1. So for that reason you got another equation saying that you have now alpha k transferred into k into alpha k equal to 1. So if the given alpha k satisfies these two equations, you can simply get that alpha k, multiply with your transpose x, your data points x, and directly you can get your whatever your final aim of getting the eigenvector. That's all. but the point is here, but there is an important point here. Okay, this is one point, but because last time we have understood one important thing, because last sessions we understood one point here, that see linear algebra fact, we derived that SVD and all. What we derived, that the non, I'm writing, okay, this, the non zero eigenvalues, wait, the non-zero eigenvalues of what, x into x transpose and x transpose into x are exactly same. Correct, exactly same, because you, yeah, similar, correct. This lambda 1 lambda 2 we calculated, and the bigger one has zero eigenvalues, because this we know that this SVD we calculated, and these singular values are like delta 3 and all should be zero, only delta 1 and delta 2 are available. So we calculated last time. So we know that this linear algebra fact, that the non-zero eigenvalues of x transpose, x into x transpose and x transpose x are exactly same, that we derived earlier. So what is that, d cross d is what, x into x transpose d cross d, and this is what, n cross n, and their eigenvalues are exactly same. Okay, and now we are using this fact now here. Okay, now we are using this fact. So we know that, okay, till now we understood we want the alpha k which satisfy these two equations. Okay, just remember, okay, don't forget these equations. It's like you don't need to mug up these things, but just understand, now we derived this equation, the alpha k should be following this, which should satisfy these two equations. Okay, now we know that. Okay, so we say that this, because x into x transpose and x transpose, this is the fact, we know that. And the maximum value of the non-zero eigenvalue, how many maximum values are there of the eigenvalues, like how many maximum eigenvalue I can take, because this is n cross n and this is d cross d. So maximum values of non-zero, okay, this is important, non-zero eigen values is equal to minimum of d cross n. So whichever the minimum in that d or n, that is the your, that are the that many numbers of maximum value, like you know, like lambda 1 lambda 2, we got equation lambda 1 lambda 2, and this lambda 1 lambda 2 has some value, lambda 3 is equal to 0, so you are not taking this 0, so you are taking, sorry, I think it's a minimum of, so how many maximum eigenvalues I can take, this is the equation, minimum of d comma n. So whichever the minimum value here, earlier in that earlier example we were like a minimum of 2 comma n, so we got 2, so we got lambda 1 and lambda 2 are the eigenvalues for that equation. This fact I am saying, that what is the linear algebra fact, these are the two facts, because you may get the some questions saying that there are two non-zero eigenvalues or there are eigenvalues of x into x transpose and x transpose are they same, different and all, or there are like multiple questions, you have to choose which are the two three options are correct. So always remember this non-zero word, the non-zero eigenvalues only, okay, not all eigenvalues, the non-zero eigenvalues of x transpose, x into x transpose and x transpose x are similar. Okay, and how many the maximum value of non-zero eigenvalue we choose, that is minimum of d cross n. Okay, so you will, somebody say I have 5 cross 5 and somebody say I have 7 cross 7 matrix. Okay, what is the, how many is the minimum maximum eigenvalues I can choose. So what is the maximum, the formula is maximum eigenvalue is equal to minimum of 5, because this is d cos d, this is n cross n, so 5 and 7, so minimum is 5. So that is the maximum eigenvalues I can choose, that 5 is the maximum eigenvalue I can choose for that solving getting the equation. Okay, this is the some fact I am saying. Okay, now we are now coming to our main important point. So we now know that here, okay, this is important, you just remember this is important. Okay, so I am using the fact now here. Yes, yes, rank matrix calculation. So you have to calculate the so you have to solve these, and you have to see that which are like totally independent lines and then rows, and then only that values gives you the yeah, that value gives the rank of that, and that's the maximum thing. Okay, So this is something you will get some kind of multiple choice questions. You have to see that kind of things, but you should know that why it is here. This is concept you should know, because we derived in last class the SVD, and then SVD gives you the 5 cross 7, then 5 is the best, or in our last example it is 2 cross 3, minimum is 2. Okay, so we know that now here. Okay, C is what? 1 cross n, 1 by n, x into x transpose. So C is the one covariance matrix. Okay, I will write down here. So I need a big box here. So C is 1 by n x into x transpose. That is the covariance matrix in normal PCA. That is what we were doing when we are not bothering about n is greater, d is greater and all. So because generally n is greater than d, so consider this equation is where the n is greater than d, this equation. Okay, this is normal case. Okay, and what are the eigen values? Eigen vectors, and here is eigen values. Okay, okay, so what are the eigenvalues for this? So eigenvectors for this. So eigenvectors are, like we know that, w1, w2, so on till wl. Okay, because this graph we just did that k, and we stop somewhere this l, so that has the maximum covariance is 95%. This here, I'm just showing this graph. Okay, just remember here. Okay, for all value of k. Okay, and what is the eigen values for this? With normally lambda 1, lambda 1 is greater than, because lambda 1 is greater, because this is maximum eigen value. Lambda 1 is greater than or equal to, lambda 2 is greater than or equal to, lambda 3 is greater than, and so on till lambda l. Okay, okay, and make see everywhere this wk square is equal to 1. Okay, this is common. Okay, means this by considering this equation, we are every time thinking wk means that the length of your eigenvector is always be unit length. If it is not, then you have to normalize it. That generally in the calculation you do that. Once you get the CSV Excel sheet data with all data, then you do this kind of calculation. Okay, but this is what the first normal case. Okay, in second case, oh sorry, second case, now if I just simply put this into here, so I am doing, see here, I am doing here nc equal to x into x transpose. I am just putting this x, because here something I am doing x into x transpose divided by n, so I don't want this n here, so I put n here. So I want this. Now this is my different matrix x into x transpose. Okay, so now this is nc. So what is the eigenvectors for this? Eigenvectors are every time same, like they are either going up, down, but the directions is always be same. In this case also, w1, w2 same, wl for all value of k. Okay, and here also same. Okay, wk square equal to 1. Okay, this is same, but here what change? Here the changes are your eigen values. So what is that eigenvalue? N into lambda 1 greater than equal to n into lambda 2 greater than equal to n into lambda n. Okay, this is the eigenvalues for this kind of a matrix. But now the third matrix which we need, what we need, that we are interested into some k matrix. We mentioned k is equal to x transpose x. This is ulta, this is totally reverse, because here what you are getting, d cross d, here you are getting d cross d, but now here you will get n cross n. Okay, this is n cross n. What you are now interested, because in all the equations what you have now seen, this k is coming here in all these equation. You can see this k, this is the k, this is the k. Okay, here is the also k, and what is k? K is what? X into x transpose. So k is equal to what? X transpose into x. Okay, which is n cross n. So in both the equations k is coming, so you need to derive some kind of so you need to derive the eigenvectors of x transpose into x. So what is the eigenvectors are here? So let's say, because that won't be w1 w2 w3, they are like, as I last time gave the example, like alpha 1 alpha 2 or u1 u2 or u3 u4, something like this. So I'm now saying this is like a beta 1 beta 2 so on beta l, where always remember this beta, whenever the eigenvalue eigenvectors comes in the PCA, they are having unit length equal to 1. Okay, and the eigenvectors, see, now only in this linear algebra we just said that the non-zero eigenvalues of x into x transpose and x transpose x are exactly same, this line, okay, are exactly same. Okay, so whatever x and whatever the x into x transpose, this x into x transpose and this x transpose into x, they will have the same eigenvalue, n into lambda 1 greater than n into lambda 2 greater than or equal to n into lambda n. Okay, this is the eigenvalues of the x transpose into x, because we know that this linear algebra fact, and then we understood that. Okay, so we now understood that this is something like the some eigenvalue eigenvector. So this equation is, so means this is going into some equations. If I just see now this, okay, means if the k is having some kind of equation like covariance matrix x transpose x beta and all, so we know that av equal to lambda v. Once again I am coming to this eigenvalue equation. A is what? Some kind of a covariance matrix. In this case, what is the covariance matrix? This is covariance matrix, correct? A is, so in this case what is that covariance matrix? X, sorry, in this case it is k. This case I am saying about, because this is what we are now interested in. Okay, this is what we are now interested in, x transpose into x. That is what we need to find out, the alpha k and that two equations where k is there. So this k is nothing but, because this is av equal to lambda v, so a means what? Covariance matrix. So in our case it is k. Okay, what is the eigenvalue eigenvectors for this? Eigenvectors are beta 1. Which line? Here, this line? This line you don't follow here? Okay. See, I mentioned, because why we understood this eigenvalue, this linear algebra fact, we are trying to, because see, x into x transpose what? It is actually d cross g. That is the problem you are having, correct? So you need something like n cross n. So you found that x into x is, x transpose x is nothing but n cross n. Okay, so you want something in x transpose x. Okay, so we are now trying to see, so instead of going to the next step to solve it, we found that what is the linear algebra fact, we got that the eigenvalues of these are same, x transpose x and x into x transpose or x transpose x are having similar eigenvalues. Okay, so here n lambda 1 n lambda 2, see here this line. Okay, so we got x into x transpose here. Okay, but what we are now interested, so we are interested into x into x transpose. Why we are interested? Because every time we are having this k, and what is k? We know that k is equal to x transpose x. We derived it now already. We derived. So in both the equations, the alpha k, we need the alpha k which satisfies these equations. K into alpha k equal to n lambda k into alpha k, or alpha k transpose k into alpha k should be 1. This equation has to satisfy that alpha k only we are interested, and that alpha k we will multiply with our data point x and we will get some eigenvector wk, and that's all PCA is done. But we need some kind of alpha k which satisfy the equation, and that equation has a k value, and k is what? X transpose x. So is there any relation between x into, is there any relationship between x into x transpose and x transpose and x? That we saw last time and we derived also. We found that the non-zero eigenvalues of both the x transpose x and x are exactly same. Okay, that's why we are now putting this equation here. So as we are interested into the k, as we are interested into calculating the k is equal to x transpose into x, which is n cross n, we are interested into that. So we said that, okay, we don't know what is the eigenvector for that, so we said this is beta 1 beta 2 beta 3, like this, beta 1 beta 2, and that has also unit length 1. But from the linear algebra fact here, this fact we found that eigenvectors of x into x transpose are same as x transpose into x. So we said that same. See, these and these are similar. N lambda 1, n lambda 2, lambda. Okay, they are like a similar. The eigenvectors are same, or the eigenvalues are same. Only the w1 w2 is different. This is different and this is different. They are not same. This is beta 1, this is w1. Okay, so you got till now here, Murli? Okay, so yeah, so what happened now here, because this is some kind of eigenvalue equation. Now we got eigenvector and eigenvalues and all, so we now know that this is some kind of eigen equations. So what is eigen equations? Eigen equation is something that general equation I am saying, av equal to lambda v is the eigenvalue equation. Okay, that is general equation. What a is nothing but your covariance matrix. In this case, what is the covariance matrix? That is the k. That's why we wrote k. Okay, we are just trying to write the eigen equation for this line. Don't consider now, don't consider like what is this line and all, but this is something what now we derived. Okay, so k. Okay, this eigen the covariance matrix is k. What is the eigenvector? Beta k. What is the eigenvalues? N lambda k, and then same way beta k. Okay, so this is the eigenvalue equation. Okay, for this this is eigen equation. Okay, for this. But you say, but we know that. Okay, but we know in general what we know, covariance matrix C, wk equal to so the earlier whatever equations we have seen, the equations is something n lambda k, sorry, not n lambda k, so here this covariance matrix lambda, okay, this lambda 1, lambda 2, lambda k. Okay, yeah, okay, lambda k w k, that is fine. But here okay, because this is important point, because we are trying to find out the relation between alpha and beta now here. Okay, so that's why I want to say here, we earlier know that with the equation number here. Okay, these are the equations we got. Sorry, so okay, yeah, because we are like I'm writing too much bigger font, so that's why if I want to just go to the okay, but like once you see the video now, so because now it is going to be end now, yeah, once you see the video you will understand later on also, or yeah. So what happened now, we were knowing about alpha k and alpha k, like we are like every time listening about alpha k. So whether this beta k, because k into beta k equal to n lambda k, oh, sorry, one second, huh? I think my 1 second, I'm not able to write that. Okay, now it's coming. I think this is a old file. Okay, I just need to, it got hanged actually. I'm just trying to scroll it down. Yeah, now it's coming. Okay, so what happened, n into lambda k it's little slow now. Okay, just 1 second. Okay, the system got hanged, but okay, so what happened, this equation here, k into beta k equal to n into lambda k into beta k, this one what we said, that this equation. Okay, this equation, you got this equation here. k into alpha k and lambda k beta k, because beta k are the some kind of eigenvectors we said. Okay, these are the eigenvectors. Can I bring the new one? The system is hang now because I cannot like use my pen. Okay. Now this is the last point, but okay, what we'll do, we'll just take 2 minutes of break, or uh, so yeah, 5 minutes we'll come back after this. Okay, I just what happened, I will open the new note here, Microsoft, because this is like, I think it's an old note here. Okay, last session also happened like, I think so, in this, so that's why it is hang now. Now I am just trying to scroll it down, but it is just hang, and now automatically it will come fast. Now it's coming. Yes, yes, yeah, yeah. Yeah, so I think there is no option of stopping the recording, but here they start recording, stop recording only here, but there is no pause. Hmm? So we'll wait for a few minutes and then we'll start. Okay. Uh, yeah, yeah, 5 minutes we'll see. Okay. Yeah. So are you guys now here? Okay, super. No, I just I just thought to yeah, this is totally, this system is hanged actually. I think I should write it here. Uh, I hope okay. See, yeah, I can write it here. Okay, so we now know that there is a for this in this table we found that we just calculated now there is a covariance matrix of x transpose into x, which is n cross n. For that there are some eigenvectors. We say that beta 1, beta 2, beta 3, where the beta 1 length should be 1. That is every time you should remember, okay, for the PC calculation every time. Okay, and the eigenvalues should be similar like x transpose x into x transpose, because we know now the linear algebra fact that non-zero eigenvalue of x into x transpose is same as x transpose into x, that we calculated last time using SVD. That's why we said that the eigenvalues of x into x transpose into x is same as x into x transpose, which is n lambda 1, which is greater than n lambda 2, which is greater than n lambda l. Okay, like so on till n lambda l. Okay, till now we are now here. So we now understood this is a one eigen equation, because k is equal to covariance matrix into beta k is like whatever the eigenvalues here, beta 1, beta 2. Okay, n lambda k, because these are the eigen sorry, beta is the eigenvectors, k into beta k equal to n lambda k, these are the eigenvalues n lambda k, and beta k is same as the eigen vectors. So we know that av equal to lambda v, that's why we can write this equation. And we found these two important equation, k into alpha k. We found these two important equation, k into alpha k. I will write these equations down. I will write this equation here. Okay, here k into alpha k equal to n lambda k into alpha k. Okay, this is one equation. Next equation is k alpha k transpose. Okay, alpha k transpose k into alpha k should be 1. You need, so this is what, these are the two basic equations. So every alpha k has to satisfy these two equations. Every alpha k has to satisfy these two equations. Then only you consider that alpha k to get multiplied with x. This x is multiplied with that alpha k which satisfies these two equations, and then we get wk, that we know. But now here new things come, k into beta k equal to n lambda k equal to beta k. New things comes here. Now because see this equation alpha k n lambda k, k beta k n lambda k beta k. So we are now thinking whether alpha k equal to beta k, is it same, is that both are similar, is this beta k is same as like alpha k. We have the question, because see here this is what equation, this is the equation what we need. We need that alpha k has to satisfy this equation, and we got that from this matrix, this calculation from this table. We got that this equation, this eigenvalue, this eigen equation. So now we need to think whether this beta k is same as alpha k, whether they are like same or different. So from this equation at least, because here from this equation of k beta k n lambda k to beta k and k alpha k, this k alpha k n lambda k into alpha k, we say that okay, that may be same because they are looks like same. But if they are same, you are saying that oh, they are same, but there is another equation called as this. There is another equation which is here, because if that alpha k is same as beta k, then it also has to be beta k transpose, it also has to be beta k transpose k into beta k should be 1. Is it that, is it this is also there? If both are same, if both are same, then it has to, these things also has to be same. Are they same? That we need to find out whether alpha k and beta k are same or not. That we need to figure out here. Okay, so now we found that from this equation. Okay, so now we found that k into beta k equal to n lambda k into beta k, that we know that. Okay, let's multiply. Okay, this equation, consider this equation as equation number 11. Okay, just consider this number. I'm not following the equation numbers, but to differentiate that, so I put 11 number. Okay, so I am just multiplying beta k with that equation. Okay, equation 11. Okay, so what it will do, beta k, k into beta k. See, I'm just simply multiplying this equation. Okay, same way, beta k n lambda k beta k. I'm just simply multiplying, I'm not doing anything different, multiplying. Okay, yeah, I'll write here, multiply beta k to equation 1, beta k to equation 11. Okay, just I did that. Okay, what happened now, we know that because beta k, the length of beta k should be 1. What is this? This is nothing but beta k transpose into beta k should be 1. So if I just rearrange these two values, beta k transpose into beta k, this one, if I just rearrange n lambda k beta k transpose beta k, this is what, this is 1 because of this, as we put the condition here, as we put this condition, the length of beta k square should be 1 in this case. That's why it is coming as n lambda k beta k transpose k into beta k is equal to n lambda k. But what here, if you are saying alpha k and beta k are same, if you are saying they are same, if you are saying, we are not till now we are not claiming anything, but if you want to say alpha k and beta k same, then alpha k and beta k same, then beta k transpose k into beta k should be 1, but it's not coming 1, it is coming n into lambda k, it's coming n into lambda k, means yes, yes. So what we can do here, we can just rearrange that now, beta k transpose k into beta k divided by n lambda k equal to 1. We can do like this here. Okay, we can do. So what is this? This is nothing but, if I just simply rearrange this, how you write 5? 5 is what, under root of 5 into under root of 5, correct? Same, correct? So same way here, like for example 7 also, under root of 7 into under root of 7, correct? So beta k transpose k into beta k divided by under root of n lambda k, then under root of n lambda k equal to 1. I am just, instead of just doing this, so I am just simply dividing by this under root of n k, just this is same, maybe I can write here for you. So beta k transpose n into beta k divided of under root of n lambda k into under root of n lambda k equal to 1. Okay, the same, and now I just simply differentiate now here, like I just put this one now this side. So we now have, yeah, k is like same, yeah, k into bk, yeah, k into bk. So k is there, yes. So I'm just simply sorry here, sorry, I'm just k bit, sorry, okay, k beta k transpose k, sorry, not this is not n, this is k, okay. So now from this equation we found that this k into alpha k, okay, k into alpha k equal to n lambda k into alpha k, this is one equation, and alpha k transpose k into alpha k should be 1. This is what we need for alpha k. So whatever alpha k satisfy this equation, we are happy to go with that alpha k. But now we are saying there is another beta k, this is not alpha k, it is another beta k for this matrix. So we are trying to think whether this beta and alpha has some kind of a relation, whether they are relating with each other. Then we, from this solution, we understood that, from this solution we understood that alpha k is nothing but what, because you know that alpha k transpose into k into alpha k equal to 1. This is what we know, that correct, this is what we know, okay. Means what is that, alpha k is nothing but, from this equation we found that alpha k is nothing but beta k under root of n lambda k, that's all, okay. So what it is saying, this is what the problem solution. So what it is saying, you get whatever now k value is, what k value is, what x transpose x, correct. So you calculate the, this is the covariance matrix, you get the covariance matrix, you got it, x transpose x is the covariance matrix. You calculate the eigenvectors of that. What is that eigenvectors? That is nothing but your beta k. And what is the eigenvalues? Eigenvalues are equal to n lambda k, n lambda 1, lambda 2, lambda 3, n lambda 1, lambda 2, like this, okay. So if you get beta, you directly put that beta here in this equation, this equation, alpha k is equal to what, beta k divided by whatever the eigenvalues you got of this covariance matrix, n lambda k, you get alpha k, and once you get alpha k, you go with wk equal to x into your alpha k, and then you get your PCA's thing, wk, that is eigenvectors. So what is this x into x transpose? That is nothing but n into n. So that's all. When earlier what happened in your, in earlier our case, we were doing d cross d, that is very much problematic. But now in this new algorithm, that's all. In this new algorithm, these are the steps I'll say you now. For this new PCA algorithm, okay, this new PCA, I will just simply say new PCA. It's not good way, correct way saying new PCA, but new PCA, maybe week 2 like this, okay. So these are the new steps. You have input. What are the inputs? You are having, okay, x1 till xn, okay, x belongs to rd, okay, so capital value, okay, because it's d, already d vectors. So instead of saying x1 like this, I say capital Xn, okay. Okay, now you have these input vectors. This is step number 1, you already got that. Number 2, then you do this mean value calculation, mean and subtraction of mean, that you do that, okay. Next is you are calculating your covariance matrix. What is this covariance matrix in this case? K equal to x transpose x, okay. Yeah, because this is what new PCA, the new PCA, like not old PCA or new PCA, okay, it belong to R. And what is this now? It is n cross n, correct, here, okay. This is n cross, and this is new algorithm, okay. Once you get this covariance matrix K, as usual we will do this eigen decomposition of K. Eigen decomposition means what? I will say eigen decomposition of K matrix, covariance matrix. Okay, what you do, you calculate. Yeah. Hmm. Yes, 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 when d is greater than n. Yes, 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 yes. So eigenvectors, like I say eigenvectors, now it's beta 1 till your beta l. Okay, and make sure, because this is what you know that the eigenvector calculation earlier it is d cube. This eigen decomposition was d cube, but in this case eigen decomposition, this complexity, this time complexity is n cube, because now you are not doing d cross d, you are doing n cross n. That's why it is n cube. Okay, this is what the, yes, I, yes, that is, and then this is eigen values are, what is eigen values, because you also get n lambda 1, n lambda 2, and so on, n lambda l. Okay, you got that. But this is the fourth step, because this is all what, this is all d is greater than n. Okay, this is d is greater than n, this is this all algorithm whatever we are doing, it is like for d is greater than n case only. Okay, so this is what you found that, okay, beta k, but what we need alpha k. What is that alpha k? Alpha k, oh, so yeah, you can do that 1 by n x transformation. Okay, so so here alpha k, okay, alpha k is equal to here, wait 1 second, it's not be 1 by n, because we derived now here. If you see this equation, we say that k is equal to what, this is our, yeah, yeah, that is our normal case, we do that. But in this, because we derived now, k is equal to, we consider k is equal to x transpose x, so not 1 by n upon x transpose x. But in this case what happened, it is 1, yeah, it is x transpose x only. Okay, so let me, okay, okay, so now we know that alpha k equal to what, alpha k is equal to whatever the beta k you are getting, the eigenvectors, maybe I'll write here beta k. Okay, this alpha 2, beta k divided by under root of n lambda k. You got that, n lambda k, the alpha k is equal to, this is what you have for all value of k from 1 to l. Okay, once you get alpha k, in the next step you simply go with your most known wk calculation, which is wk equal to x into your alpha k for all value of k. Okay, from 1 to l. Okay, so this is what the algorithms of, hmm, yeah, yeah, vectors only. Yes, if beta k is not the final RWK, because we know that beta k and alpha k, because we found that there is a, it's not same, like alpha is not same as a beta, they are not same. So how they are same, they are like beta k divided by n lambda k, once you do then they are same, alpha is equal to beta upon n lambda k. And then next step is the wk is not same as alpha k, wk and alpha k is not same, because they are not same, because see yeah, yeah, all are eigenvectors only, but they are at different state. Okay, this is wk is what, d cross d, and this is what, n cross n. Correct, and this is from this we derived, maybe this derived this beta k, from this we derived beta k, because we know that we understood that beta k is like this beta k upon n under root of n lambda k. So this said that this is alpha k, and this alpha k are like, yes, Yeah, and that n cross n, then we derived this wk, which is d cross d. Like, don't need to calculate d cross d because we calculated wk by using this matrix, which is here. So this is the step. So in the exam, maybe like the questions comes and you can like see they will say that here d is greater than n, and then because these are like multiple choice questions, you can solve it like this. Like, what is alpha k? Alpha k is what? Like beta k divided by n in beta k divided by under root of n lambda k. This is the alpha k equation for all value of k equal to 1 to n. And what is wk? Means that is your final PCA eigenvectors. So all the night, this is the movie's climax now. That's all. You are trying to figure out wk, which is eigenvectors of your complete wk is like a best line. This is complete data set. Whatever you are having, you are trying to figure out the best line for the data set, which is wk. But wk is not immediately easy to find because it's d cross d. Dimensions are d is greater than n. So that is problem. So what you said that I want to see that x into alpha k. So we thought that okay, alpha k has equation xi transpose wk divided by some equations we were having earlier, correct? Xi transpose wk divided by n lambda k, and you thought that I need wk and alpha k is having wk in that equation. I don't want to take that alpha k equation. I will choose some other equation. And then you started deriving the equation and you figure out, instead of getting direct alpha k equation, what you got? You got two important equations that alpha k has to satisfy. What is that two important equation? One is your the equation is k into alpha k equal to here. The two equations are here. These two equations, these two equations, k into alpha k is equal to n lambda k alpha k, and alpha k transpose k into alpha k equal to 1. These two equations alpha k has to satisfy. Then only you will choose that alpha k. Okay, but you said okay, now is fine, like you are happy with that. But then problem is, whatever the equation or solution you are getting, that is of x in x transpose into x, and then you figure out okay, whether this x transpose x having the same eigenvector which should I call as alpha k or not. For that reason you try to derive, because we said that new eigenvectors as beta k. So we started with considering whether beta k and alpha k are similar or not, and we calculated this equation this way here, the equation number 11 and this 12, this, and we figure out the alpha k. We figure out here finally the alpha k is equal to beta k divided by n lambda k. Means whatever the eigenvectors you calculated for x transpose x, like which is n cross n, whatever eigenvectors, these are actually beta k vectors, and from that beta k, whatever the eigenvalues you are having, you take a square root of that n lambda k, you take a square root of that and divide this beta k divided by the square root of this, you get the alpha k. Once you get alpha k, that's all. Once you get alpha k, you will just multiply with the actual data points. Like these are the complete matrix. Okay, this is not one value, it's a complete matrix. Okay, okay, because see why if I just give any name, because sir has used alpha k beta k name only in this, so that's why I just put that name. But if you see these actual videos now, then you understood that how we got this alpha k, because if I just say you that at the earlier steps, uh, yeah, yes, yes, yeah, yes. For example, now here we put that name as alpha because there is no special name. Yes, yes, here if you see this equation, yes, yes, so see CWK, yes, yes, yes. So we just thought that this name as alpha, and then we understood that because alpha is some, this is one kind of eigenvectors but with some different equation. Yes, yeah, means like constant, some name variable you say instead of constant, because constant will be not the correct name because these are the eigenvectors. So that won't be any constant term, but it's something like some kind of a variable or a group of variables. Yeah, yeah, yeah. Yeah, this is like a vector, eigenvectors of some equation that you don't know. Like you have to derive the equation, and then we derived that this equation number here 8 I just mentioned, this equation. So your alpha k is the eigenvector of this equation, this k alpha k n into lambda k into alpha k, this equation number 8. So consider it like this, and then we found that okay, there are two equations we got. So these two equations are what? These two equations are your here this k into alpha k is m lambda k into alpha k, and that unit length 1. So unit length 1 means you need to figure out the another equation, which is here, this equation, alpha k transpose k into alpha k equal should be 1. This is the another equation. So you have to have these two equations for your alpha k. So here I have written these two equations here, these two equations I have written here. Okay, so you have to have this equation number 1 and equation number 2 for alpha k. But the problem is, whatever the x transpose x gave us the eigenvectors, they are not the direct alpha k, they are the beta k. So that's beta k and alpha k should have some relation. So we try to figure out the relation, and we found that alpha k is nothing but your whatever beta k means the eigenvectors of x transpose x you got, that eigenvector divided by its under root of its eigenvalues are nothing but your alpha k. And once you get alpha k, you know that now once you get alpha k, you know that now you just multiply with your the data set, data points, you get your wk, which is nothing but your eigenvalues of your finally the PCA. And this wk you can take happily, and you can just like go and draw your best line, and then you can just put all the points on that line to make sure that that line gives the maximum variance, and that line has the minimum proxy distance, summation of minimum proxy distance. That's the best line. So that's all your PCA is done here. But there is another issue number 2 we have to solve, but this is what the issue 1. So any questions till now, any question, because this is important. We'll take next 20 minutes and we'll stop afterwards. So tomorrow we'll take last solution for this week too. Okay, so any questions? So we can like ma'am, do you have any questions, ma'am? Okay, okay. Okay, so the point number 2. So maybe now I'm not continuing with the same note. I will just open the another one. Okay, so we solved our issue number 1 when there is a d is greater than n. So when d means dimensions are greater than your number of data points, then you have to figure out another way of PCA, which is nothing but here. Take the input, like same way you need to calculate the mean of that, get your like center data, and once you get the center data, you need to calculate x transpose x, which is the covariance matrix, and afterwards you have to calculate eigen decompositions, calculate the beta eigenvectors and n lambda 1 eigenvalues, and once you get beta, then calculate alpha, which is nothing but beta k divided by under root of n into lambda k, that eigenvalues of that matrix, k into k, x into x transpose into x matrix, covariance matrix. Once you get alpha k, then multiply that with your actual data set to get final eigenvectors. This is the solution of your issue 1. So whatever the alpha k you are getting, these all are actually n cross n, all are n cross n, n cross n. So that's why instead of doing d cross d, because d cross d is what the covariance matrix, and calculating eigenvector and eigenvalue for that d is greater than n, it's very time consuming, which is d cube. But now here you need n cube kind of a time complexity. That is what you were trying to achieve, and once you achieve that, you use this beta k, these formulas, and then you derive that. Finally you derive your new eigenvectors, which is x, like capital X, which is the data points into your alpha k value. So hence you can get the best fit line. That's all your new PCA's steps where d is greater than n, and here time complexity is O3. n3, time complexity O is equal to n3. Okay, this is your issue 1. Now the next issue is nothing but issue 2, issue number 2. What is that issue number 2? We are now checking. Okay, so I hope there is no issues for you other than this PCA issue number 2. So I'm just starting with the PCA issue number 2. So PCA has the next issue, that when there is a non-linear relationship among features, like features are not having, because earlier we have seen that our features are like always be falling somewhere like this. They are having some, like how this value is growing, these points are also going, like how the height grows, weight is also growing like this. So they are having some kind of earlier PCA having this kind of relation. But when they are having non-linear relation, that we are now figuring out. Let's say you are having, let's say now here you are having some points which are something like this, which are not linear. Okay, there is something a comma b. Okay, they are like, they are having some kind of circular relationship, like you know the equation of circle is x square plus y square equal to a square, or r square, like radius square. Okay, something like this. So you got the data which is non-linear, having some kind of this type of a spread, or this kind of a relationship between the points here. And they ask, like you are a data scientist and your role is to find out the you have to compress the data set using PCA, for example, and you need to find out the PCA on that. So what you do, you get the data, our general steps, what we know that our general steps, what once the data is like not center data, you bring the data as a centered one. So what you do in next step is you bring all the points here once again back to your 0. Okay, this point, step 1, like you got the data, centered data, okay, subtracting mean and all, calculate the mean of this value, and you got the centered data. Now you are saying that okay, I got the centered data. Okay, now centered means origin is equal to 0 comma 0, this a and b become 0 and 0, so centered data, you get the one baseline. Okay, you got finally one baseline as w1, like this is with your w1. Okay, line L1 with eigenvectors at W1. Okay, and next W2 is perpendicular to W1. Okay, eigenvectors W2, that line next line next line is L2, like this. Okay, but the problem is what with this, what is the W1? W1 is best for what? These points. Okay, this W1 line best for these lines, like whichever is very near to this, but not good for the line which is something here. Correct, but this is best for the line which is near to that point, because it's a circle. The circle has the same issue for all the points for this line. Okay, so you consider, okay, that's fine, this is the proxies you plotted, this is fine. The proxies are good for the points which are, the proxies are very good for the points which are here nearby place, because they are having minimum error distance or minimum proxy distance, is very good. But the points which are away, it's having issue. The same way for W2, you are having these points, these proxies, which is also good for W2. These points are projected on this line W2 or L2, like you can say. This is fine for them, but the points which are away, they are not good for them. Like this line is not at all good. But still, because for circle, whatever may be line I will draw, for circle, if I draw like this line here and here, for that also the same issue will come. If I draw like this another line, same issue will come, W1 here, W2, same thing. Okay, the same issue, because this is circle points, they are like, Okay, okay. So okay, for example, okay, now you got this data, correct? This point number one you got, correct? This point is considered. Okay, so what we generally do, we got the lines here, so we plot our proxies like this. We plot the projections or proxies, correct? You got now, you got this point, correct? This one, this perpendicular line you follow. This is this, if this is the best line, okay? But in circle, if there is this is another point, okay? Now I will just plot some points are like circular, okay? For this point, it's the smallest distance. This is what, this is the smallest distance, correct? You got this, Murli? This is the smallest distance here, okay? So yeah, yeah, so these projections, this error or these projections are having smallest distance. You are happy because for that point this line is best line, you will say, because this has a very small distance. But what about this point? Because you mentioned for the circular data, the same L1 line is best for complete circular data, circular points, whatever these points, okay? There is not as one line, there is no as a separate, like if I consider this L1 line, it is best for this but not best for this, because see, this much is the big distance, this is not best, but still you have to use that same line. So what happen, if I take consider for these lines, these dots, more error, so these are the errors, okay? This is the error, but you cannot skip it, because if I just, for example, for these points, if I draw something like this line, oh okay, so if I draw, error should be small, error should be small, variance should be high, yes. So variance should be high means your data should have more spread, that is called variance, okay? The data should have more spread. So what happened, for these points you are just projecting on here, but for the same, if you project here, if you see these points, so it will just fall on this, and if you just actually see the points here, the projection is more on this side line rather than on this line, so here the variance is less, so that's why you choose this line, this horizontal line, like this line, okay? That's what the PCA we learned earlier, this one. So in this case what happened, this is the current issue. What happened now, the problem is in circular case, whatever line you will draw, this issue, same similar issue will come, because for this L1 line, for this L1 line and for the given point, this error is less, which is very good, but for the line which are like here, the points which are like here, the line is not good. But what happen, what we'll do, but if I just draw some other line like this, maybe these points are happy with this, but what happened for these points, the error is too big for this L2 line. Yes, yes, that point, that line is like, for the circle there is no one special line, there is no one special line, because this line W1 will good for these points but not good for these, here these points is good for these points. But here same way, if I say W2, it's good for this line but not good for these kind of lines. Means in circle there is no single eigen vectors, or there is no single L1 line which gives the maximum variance, or which gives the total like less amount of proxy lengths. So we have to actually deal, if you want to calculate the PCA for this kind of a circles which has a non-linear relationship, then this kind of a normal PCA won't work. That's what I want to say. So this line, if I'm having line with W1 and this line with W2, for example W2, what W1 and W2 is calculating variance, correct? Variance should be maximum, variance should be max, and sum of error should be less, yeah, less or minimum, okay, correct, minimum, okay? But in our case what happened, consider W1, then it is this kind of variance is max, because it's a circle, so variance is max for W1 we consider like this, and W2 is second max variance. So but both are like a circle, so both are generally having the same variance, because this is like a circle points, all are like same. Correct, correct. So correct. It's like going, and all the points are like, these points are good for, maybe for these points it is good, but here these points are not good for, they are not happy with this line, but still okay, because same happen with the W1. These points are very much happy with them, W1, but the points which are here, they are crying, they are saying, oh, but in this is circle, that's why we are accepting. But we are like, we are not accepting, but this is the way. Then if you are using with a normal PCA thing, if you are saying that PCA is good for everything, then it's not correct. PCA is good for maybe linear things, but not that much easy or good for the points which are having non-linear relationship. So here I said k equal to 2 because I consider W1 and W2. I am happy with W1 and W2 because I am getting with W1 and W2, I am getting 95% of variance. So I'm just stopping at W1 and W2. I don't want to go with the W3, W4 because I got a maximum variance in W1 and W2. Let's say like this. But no, means like in this case, in this case, no, not 4, because see, this is the same direction, correct? W1 is the same direction. So this is not the next direction you need to see. This is one more direction, W2. So you don't need to go calculate one more here, W1, because it's the same W1. So for example, we consider this is a, yeah. So we consider W1 and W2 only that two directions which give the maximum variance. Okay, 95%. But is it true? Is it true that we get that's sufficient, or do we need like a two variance? Because see, W1 has the same issue for this point, correct? These points are projecting. This point is projecting on this. They are having same issue. These points are happy. These points are happy because it's okay. But this point has same issue. And for W2 also, W2, if I am projecting this here on W2, they are also having same issue. So do we need W1, W2 both, or you are happy with W1 because both are giving same kind of variance? This is circle. They are giving the same variance. What it will do? W1 will give variance like this because it's a circle. So it will fall. The points will fall like this. Correct? Because this is the diameter. Correct? This is the W1 diameter. What happened to W2? W2 is something. So it will also give you the variance like this, because all points are falling. These are the projections I am showing. Okay, W2. If I just show you this circle like this, all are projecting. The points are projecting like this from the points, projecting like this. Okay, that's why I'm just highlighted this value. Okay, and here also this. So both are having same variance, that same distance. Like consider this is diameter d. D is the diameter of your circle. Same way the diameter is also same here. So you really need W1 and W2 because in one diameter itself, in one W1 itself, you achieved same level of D, this much same length of your variance. In another W2, you are achieving the same variance which is of length D. Do you need that W2, or are you happy with W1? So this is the question now. So this is the point which we need to figure out. Do we need to have two directions here, W1 and W2, or we are happy with the single directions, or you need more than two? If this is like a non-linear equations, like I just gave you the circle equation, if it is like different parabola, and also the dimensions will be more like more W1, W2, W3, you need to get more values there. So we need to figure out how many directions, or how many, like directions mean W1, W2 times thing. So how many directions we need to calculate? We need to figure out this one. So here, now this is like a circle. What we are now seeing, this relationship is like a circular relationship. Okay, so here the features whatever we are showing, so has this kind of a relationship which is like a f1 minus a square plus f2 minus b square equal to your r square. We know that this x square plus y square is the equation of your circle. Okay, so and with what we said, this x square y square is origin, we consider origin as 0 0, but if the origin is a comma b, then this is the equation f1 minus a square plus f2 minus b square equal to r square, because these points which are here, they are following some non-linear relationship, and in our example they are following some maybe circular relationship. That's why we mentioned they are having this relationship of f1 minus a whole square plus f2 minus b whole square. Just we need to solve this f1 square minus 2 f1a plus a square, this equation I am solving, plus this f2 here, f2 square minus 2 f2b plus b square, and just I'm bringing r square inside. Okay, r square inside equal to 0. Okay, I just like solve this square, which is like a normal things what we generally do. Okay, f1 square plus, I'm just now bringing them together, f2 square minus 2 f1a minus 2 f2b plus now a square. Okay, a square. Ma'am, can you repeat it because I did not hear you properly? Generally, like the equations of the circles, the equation of the circle we write like this. Like this is the what we write now, y equal to mx plus c, equation of a line. You write now like this, y equal to mx plus c, or parabola you say that ax square plus something like a x square, like this. Correct? So this is the equation of a circle, x square plus y square equal to r square. Generally we write in math the equation of a circle is x square plus y square. But when we write x square plus y square, instead of x square, x and y, we take as f1 and f2. Okay, x is f1, y is f2, like this. So what you said, f1 square plus f2 square equal to your r square. But now you said that these points are not, for example, these points, whatever now first attempt we have seen now, these points here, a and b, they are not actually at the center. This circle is not at the center, and you have to do the PCA on that. Okay, so you followed the step, you bought it at the center by reducing the, subtracting from the mean and all, subtracting the mean from the values. But before that, when you get the question, then your problem was this kind of situation, this situation, your points were at a comma b location, the center is like this, and your points are spreaded like this. Okay, the circle way. So that's why to get this equation of the circle, this equation of the points, you are now saying that the equation of point is f1 minus a whole square. A is the location of your here, a comma b, this is the a comma b. Like now we need to derive the PCA, we need to derive the PCA for this. So consider I am not started now PCA, I am just firstly deriving the equation of this circle. Okay, now we are not yet started the PCA, for example. Okay, you are now at step 1, you got a step 1, and you are trying to get the equation of that, equation of this line, because you know that we were trying for this, but now this straight line, this w1 straight line is not good. So you understood that okay, it's not good, so it's not meaningful to do PCA on this. So we have to do something different way to do the PCA. So what is the something different way that we are trying to figure out, how we can do the PCA on this kind of a stuff when the points or the features are non-linear. They are not linear equation, they are not linearly spreaded, or they don't have linear relationship between each other. So if they are like having non-linear relationship, so we have to find out how to do the PCA calculation on this. Okay, so for doing that, we are like, don't consider we are now started at PCA, we are now just at some level, we did not enter inside the room where the PCA discussion is happening, we are somewhere outside. Okay, we are not yet now going inside, we understood the problem. This is the problem of PCA, like I mentioned, you know, w1 and w2, I said that this is a problem, you guys were with me and we were discussing in the room, and you guys thought that okay, it's okay, then you come out of the room. Okay, now don't think about anything, now consider your points are with a and b center, and points are spreaded like this in the graph. Okay, this is your graph, a and b, and you were with me in the room and you understood that PCA is not possible, like PCA has a linear relationship, it's not possible on this kind of a non-linear data set, and you are like a research guy and you have to figure out how I can do PCA. You are interested in doing PCA, but how I can do, because these are the non-linear relationship having these points are having non-linear relationship. How to do the PCA on this? So you thought that okay, start from the scratch. What is this? This is a circle. This is a circle with point A and B. So how we can write the equation of the circle? F1 minus a square plus f2 minus b square equal to r square. This is the standard equation of the circle. This is like normal circle equation. Okay. So here what we say, so any points on this circle will satisfy this equation. So whatever the line you put, any point you put, it satisfy this kind of a equation, f1 minus a square plus f2 minus b square, that it comes to the r square, that comes to the radius square of that circle. Okay, it satisfy all the points on the circle, that's on the sphere, that satisfy this kind of a equation. So what happened now, the square things, I just solve this a square minus b square. Okay, what is a plus b square is same a square plus 2ab plus b square. That same equation I just solved it, and I bought r square before here. From this equal to I square, I bought r square equal to, so equal to 0. Okay, and now I am just bringing all these f1 square together. Okay, this together, a square plus b square, because see a square, b square and r square, I am just bought all these things together. Okay, so you understood like earlier, you know that linear relationship means what? Y is equal to mx, means like line. That is what you say is a linear relation. So c is 0, this is going to the origin, so I put c is equal to 0. So this is what the linear relationship. There is no square terms here. No, for this equation I am saying, this one here. Yeah. Okay, so y is equal to mx plus c is the line equation. Okay, this is a linear equation, normal linear equation. But once maybe I will write this one as equation 1, this one as equation 2 for your guys. In equation 2, if you see, this is f1 square. What is this? F1, this is like a, you know that this is parabola here, correct? Convex shape. How you you know that here, how you draw this, like this. X square is what? Like this parabola, correct? You guys did in M1 M2 this stuff. How x square, this is what the graph of x square means. They are not linear. Okay, they are not linear, they are like having this kind of a non-linear relationship. When there is a square term come, always remember, if there is no square term, or there is no x into y or something like this, okay, there are no two variable together, x into y, then it is always be linear relationship. You can do maybe m into x, like constant into x is fine, but if there are like a two different point, x and y together, means x is 1, y is 1, that having 2 as their maximum dimension. So like this is the another thing which is like non-linear relationship. So here f1 square, f2 square, they are showing some kind of a non-linear relationship, like the parabola or something like this. Okay, means equation 2 is not linear relationship, because you already know this is circle equation. Circle is not a linear, so it's completely non-linear relationship equation. Okay, so in this case, so this is my equation. So we consider, okay, this is what we got. Now this is the main thing about kernel PCA. Okay, this is the main thing. So if you don't get the things, ask me now. Okay, so this is one equation you got. I consider this as a circle. Okay, this non-linear relationship as a circle. Maybe some person in some videos on YouTube, or some research person, scientist has also given the PCA, kernel PCA with the maybe parabola relationship, or some kind of a logarithmic relationship, or anything. But for us, or for our our MLT subject, we consider this as a circular non-linear relationship. Okay, so what we need now, this has a non-linear relationship. So we consider each and every point showing some one kind of a dimension, just like don't give more stress on your brain. Just consider each and every point is showing giving some kind of a dimension. So here f1 square gives one dimension. One dimensions means like we can like we see the things in 3D. So in 3 dimensions we can see. So like something now consider f1 square is giving one dimension. Okay, don't think more, just because next point you will understand what I am saying. F2 is also giving another dimension, same dimension. Here this f1 and f2, they will also give me another dimension. Each point, each here, each value here is giving me some dimension. Consider like this. Okay, they will give their own, like f1 is having its own dimension and f2 is maybe something different. Okay, okay. So for yes, yes. Okay, and here there is no, like there is also be f1 f2. Okay, f1 f2, but here in this equation, equation number 2, it is multiplied by f1 0 into f1 f2. Okay, this show f1 f2 show ellipse type of dimension. If you show see like this, it looks like this. Okay, but this also has one kind of a dimension. It is actually multiplied by 0, so you cannot see in this above equation. Okay, 1 2 3 4 5, and these a square plus b square minus r square also give 1. Okay, because this is like a constant, it also has a one dimension. Okay, so there are like how many, 1 2 3 4 5 and 6. So you are having f1 and f2. Okay, you are having f1 and f2 like two dimension things, and then these two dimensions f1 and f2 only in your input. Okay, and you consider this f1 and f2, and that f1 and f2 showing some kind of a circular relationship. So that circular relationship is nothing but this one, f1 minus a square, f2 minus b square equal to r square. So this f1 and f2 is showing circular relationship. And if you actually see that, so these, if I get the final here f1 square, the equation number 2, if I see that, so these f1 and f2 two dimensions are now converted into 1 2 here, 1 2 3 4 5 and now 6. So it is now here in 6 dimension. Normal earlier f1 f2 which show non-linear relationship is having this 2D, oh sorry, this 2D is now presented in 6D. This 2D is now presented into 6D. Okay, don't consider now more. I'm just like, don't stress your mind. Just we you are not now at PCA. Yes, so f1 f2 only two dimensions, but as they are showing you non-linear circular relationship, and we calculated simply the formula f1 minus a whole square f2 minus b, that is circular relationship formula. We derived it and we found that from equation number 2, these two equation, okay, these two equation number 2, we found that this f1 to f1 square f2 square minus 2 f1, these all the equations we found that, and this 0 into f1 f2, because as it has 0 coefficient, so that's why it's not visible here, but it's also be present because generally in 2 dimensions, maybe I will just write this way. uh, 1 second, I'll take the call, I'll come 1 second. Okay, important things, very interesting thing now. Okay, don't think about we have started with PCA. Okay, this is something generic. I am saying if you understood this point, the kernel PCA will be the easiest thing you will understand it. Okay, so what it is saying, that this non-linear relationship between f1 and f2, these two variables are there, f1 and f2. Non-linear relationship means they are having circular non-linear relationship. We derived it and we found that the equation 2 has, like we said that, okay, let's put each here quantity here, each variable, each equation or each point as one dimension. So we got that there are totally 6 dimensions, because if I here for your understanding I will put here 0 f1 f2 just to make sure that it is same as what I have written down. So this 2D f1 and f2 is now considered as a 6D. Okay, earlier it was just simply 2D and now it considered as a 6D. And you will say like how does 2 is become 6? Can 2 become 20? Yeah, like you don't know 2 become 20 also, 2 become like 18 also. So how it become 18? Like you are simply sending that two parameters from the lower dimension and you are projecting into the higher dimension. So maybe it's difficult to visualize, but mathematically I can say in general, okay, quadratic in two variables, quadratic in two variables, f1 and f2 are the two variable. Okay, f1 and f2 in our case, okay, has 6 terms. And if I just consider this, what are the two variables here? So here has 6 terms. Okay, these two variables are f1 and f2. So what are the 6 terms is something like a into f1 square plus b into f2 square plus c into f1 f2 plus d into f1 plus e into f2 plus some kind of a constant, like I say f equal to 0. That's why this 2D is now projected on 6D, or 2D is now considered earlier only 2D. f1 and f2 are now having these f1 f2. Okay, I'll just highlight red color, f1 f2 f1 f2 these. Okay, this is constant, finally the constant, that r square we got it na, so that r constant value f. So now these 2D points are now having 6 dimensions. Earlier it was just we consider only 2 dimensions, and now they are actually having the 6 dimensions. So in this earlier equation, this equation what we got, equation number 2, maybe I will write the equation 2 once more down here. f1 square plus f2 square 2f1 minus 2f1a f2a, okay, minus 2 f1a minus 2 f2a plus f 1 second, let me see that f2b, okay, correct, f2b, okay, then a square plus b square minus r square equal to 0. And maybe you can write like 0 into f1 f2, because this is 0, that's why is okay, like we can show that 0 into f1 f2 just to make its present. Okay, so these whatever now we have written, this is called as feature map. Okay, this is called as, because I simply converted that f1 and f2 and their non-linear relationship, because it's circular. That's why I use that circular equation of f1 minus a whole square plus f2 minus b whole square equal to 0. I use that r square, that is circle equation. Okay, circle equation, that is called as circle equation. Okay, so I consider that two dimensions f1 f2. Okay, I consider that two dimensions f1 f2 and I just created. uh, what happened? Oh, I'm able to write by this, and pen is not okay. Mouse I am able to write, but now it is the pen. Hmm. Okay, no problem. Let's try to do it by mouse as of now. Okay, so I'm just sorry, ma'am. Can you please? It's all about yeah, week two. Uh, it is week two and week 2.3. Okay, week 2.3. So this is important for concept for the kernel PCA. So see, this problem is also be there in the SVM. Okay, if you understood this, then your SVM will be also be easy. Okay, because SVM will also deal with the non-linear relationship. They will also have some kernel functional kernel way of solving this. So if you understood this, the next points or next future weeks will also be easy. Okay, so what now here we understood that f1 and f2, we just got this equation. Okay, so in this equation, if I just now try to get f1 comma f2, if I'm just like right now this big equation I will try to write in the normal vector format. Okay, firstly I will try to write the coefficient which are coming here with this constant, which is like a square plus b square minus r square. The coefficients are 1. Okay, because 1 into a square b square minus r square will be same. Okay, next okay, next point I'll try to write with like as it is here, f1 square. Okay, next f2 square as it is. Okay, because this is I'm trying to represent this f1 and f2. Okay, this f1 and f2 I'm trying to represent in the form of f1 and f2. Okay, so the third one here, because this 0 f1 and f2, so I will write here f1 f2. Okay, so next one f1 f2. See, these are like all these are like a 6 dimensions, 6D. See, the dimensions is like the 6D. Okay, so here you don't need to consider like how these come, because I just mentioned you this here, this a equal to here. If you see this ab square, so generally whatever the two dimension things you are having which has a quadratic relationship, two dimensions or two variables f1 f2 which has a quadratic relationship, non-linear relationship, which give you the 6 terms, and the 6 terms are something like this equation, like you know that y equal to mx plus c, or a square plus bx plus c, but these are like in terms of only one variable x, but here are the two variables. So the equation will be a f1 square b f1 square c f1 d f1, so f1 f2 f1 this f2, and this is constant equal to 0. Okay, and if I just do if I just get that feature map for this equation, so this is like a feature map. So I am just trying to get the feature maps, which is like I am saying that this is the one mapping, or this is one kind of I cannot say weights, but these are something which are like coefficients of the 6 dimensions vectors, or 6 dimensions no, points. Okay, 6 dimensions points. Like generally, if there is no what you consider, we are not hearing about anything about these points, whatever now we saw it here. Okay, don't consider like, you consider now these points here. Okay, whenever there is a 6 dimension things comes, af1 square bfn and all this equation comes, whenever this equation comes, it has 6 terms. And if you want to write the feature map for this, feature map means you are trying to write in terms of f1 and f2. Okay, so that you will write like this: 1 f1 square f2 square f1 f2 f1 and f2, like this is like normal. Okay, this is like a normal. But now in our case we have, see, we have our case another vector u, like consider vector u here. Our vector is u. Here it's little difficult for you to understand, but just get it. Just if we'll discuss the points, or we'll discuss your questions also afterwards, but you try to see here what is this exactly happening here. So once you get that, and it's easy for next point, but we'll see now here. So u is like, so whatever u is now, so this is like, we call this as a feature map. F of x is a feature map. So any 6 dimensions has this feature map: 1, f1 square, f2 square, f1, f2, f1 and f2. This is 6 dimension feature map. Don't relate with the PCA or anything. This is for constant, like a square b square minus r square. Now, so this is for constant, any constant for this equation, like this equation now. Okay, this f is there now, this constant. You can see this constant f. Okay, for this constant I consider this as a 1. Okay, and then f1 square, f2 square, f1, f2, then f1, f2 here. Okay, this one. Okay, this is called as feature map. So now on this feature map, this is a one feature map. So you are trying to get our this equation. Okay, equation number this. I will try to maybe get this equation: f1 square, f2 square minus 2 f1a minus this is like minus minus. Okay, minus f1a minus f2b. And how we got this? We know that these are the circle, so we got this equation number 2, like circle with f1 minus a whole square, f2 minus b whole square equal to r square. So we got this equation number 2. So how you get like here, f1 square, maybe let me write this equation. If I can copy it, can I copy this? Okay, I don't know how to copy, but okay, f1 square, f2 square, 2 f1a, f2b. Once again, this, did I write? Oh, okay, I write it here now already. I wrote it here. Okay, I wrote it here already, this equation 2. Okay, now how you will get constant value, when you multiply with this equation. Like you are trying to get this equation number 2 from this line, like this is the equation and this is a feature map. You are trying to f transpose x, you are trying to multiply this u to get your this equation. How you get? This is 1 is what? 1 is your constant. What is your constant in this equation number 2? Okay, in this equation number 2, your constant is what? A square b square minus r square. So if you multiply 1 and a square b square r square, you will get a square plus b square minus r square. Okay, now here the next term is what? f1 square. You are having f1 square, here also f1 square. So there is no problem, you can just simply multiply by 1 to this. 1 into f1 square, you will get f1 square. Here next term f2 square. So stay here for the f2 square, same here f2 square. So just multiply by 1, no problem. What happened? f1 f2. Now you are having f1 f2, but there is like a 0 term because there is no f1 f2, or it is multiplied by 0. If you want to get that, you just multiply by 0 here. 0 into f1 f2, you will get this value. 0 into f1 f2 like 0. Okay, next term is f1. Now you want this value minus 2 fa, and you are having fa. What you want to, with what you want to multiply to get f minus 2 fa? Minus 2 f1a. See, here we are having already f1, correct, and you want minus 2a into f1. So you just need to multiply with minus 2a. Minus 2a into f1 minus 2a into f1 give you minus 2a f1, which is here. Same way for f2, same way, minus 2b. Okay, so from here you got a vector u. How you got? This is feature map. This feature map is always be there for the 6 dimension things. It's not related with anything like PC or not. It's not related with anything. It's common. Okay, it is common. the feature map is there which has this type of coefficients 1 f1 square f2 square f1 f2 f1 f2. Okay, there is no comma here. Okay, 1 second. Oh, I don't know, let it be. Okay, so this is what f1 f2. Now you are interested in getting the equation number 2. How you get the equation number 2 from this feature map? Like you are trying to multiply the feature map. The feature map is phi of x, okay, phi of x is the feature map which is like 1 f1 f2, and this equation number, maybe I will write equation number 3. This is the feature map for 6 dimension. Okay, you are trying to multiply that with some vector u, so you will get equation number 2. How you can multiply? This is constant term. So what is the constant? A square b square minus r square. So if I just multiply 1 and a square b square minus r square, I get this term. I am happy. I am already having f1 square and also f1 square, means I just need to multiply with 1. So I will get f1 square. I already have f2 square here in the feature map. Just multiply with 1. So I can get f2 square in this equation number 2. Now I am having f1 f2, but there is no f1 f2 in this equation number 2, this equation, because this is 0. So just multiply with 0. That's fine. There is another term as f1. Here also there is one term as f1, but it comes with minus 2 into f1 into a, means like minus 2a is the coefficient with the f1. So minus 2a is the coefficient with the f1. For f2, what is the coefficient? Minus 2b is the coefficient for the f2. So now if you do phi transpose x into u, this is showing the linear relationship. If you do like this, then you will get, because c is equal to 0, that's why I mentioned equal to 0. So if you just show if you just do phi transpose x into u equal to 0, that is what? That is the linear relationship, or that shows the linear relationship in the new dimension. Okay, just be there with me. Okay, so what happened? The first point, okay, the first point, whatever we are having f2 and f1, like f1 and f2, what is the dimension? Murli sir, what is the dimension of f1 and f2? Like there are two f1 and f2, so it has two dimensions. In two dimensions, what was the relationship? The relationship was f1 minus a whole square plus f2 minus b whole square equal to r square. This was the relationship. Is in the two dimension, this was the relationship. Is it linear or non-linear? It is non-linear relationship. Okay, it is non-linear relationship. That's fine. It's non-linear relationship. Okay, in two dimension. But if I go to 6 dimensions, why 6 dimension? I can go to another also, but in generally quadratic in two dimensions or two variables, quadratic in two variables f1 and f2 has 6 terms. That's why we go to 6 dimensions. A f1 square, b f2 square, c f1, d f1, e f2, f like constant equal to 0. That is the quadratic terms in the 6 dimensions. So two dimensions in the, like two dimension means f1 and f2 in the lower dimension has non-linear relationship, which is here, that is called as lower dimension. This has non-linear relationship here. But the same thing, if I go with the higher dimension like a 6D, that shows phi of x transpose u equal to 0, that shows me linear relationship. Okay, that shows me linear relationship. So what happened now here? This is important in the kernel concept. What happened? Like maybe consider like a person is maybe maybe there is one person from X country. Okay, so his currency is something like okay in his country, like he is okay with his currency. But if you go with his currency, maybe a person from America, he is working XYZ, he has dollars. Okay, his dollars are like a 2D. Consider, don't map okay money to this. Consider it's a 2D lower dimension. If he come to, if this same guy come to Africa, okay, African currency, so same, if he has $2, now it become 2 into multiply by their African currency. Maybe consider, for example, consider their 1 rupees is like $1 is equal to 200 their currency, for example. Okay, 200. So he has $2, so in his currency it become 400 in African currency, for example. So what is happening? So the person who is okay or normal or poor in his country, he is become rich in Africa. The person is having dollars, same dollar, okay, in his country, $2 only. He is okay, poor in that country. But once he go with the same amount in Africa, he become rich. So the person, or so the relation of F1 F2, which is non-linear in his country in 2 dimension, he is non-linear. Once he go to higher dimension, he become linear. Okay, so maybe it's difficult for imagining, but consider like lower dimension, whatever the lower dimension things are there, if they are showing non-linear relationship, you bring them to higher dimension, they will show you the linear relationship. So what happened in lower dimension, we are having F1 and F2, which show the circular relationship, which is here whatever we just whatever I have just highlighted here. This is the circular relationship in the 2 dimension things. This is non-linear. But what happened? This circle, the circular relationship is non-linear. I brought it to higher dimension. I brought this one to higher dimension. So this 2D is brought it to 6D, and this is non-linear relationship of this 2D, which is maybe circle, is now, okay, this is circle. In 2D it is circle, okay, but the same circle, if you see this one, what is like, for example, if you see this is like, for example, this is kind of a cone, okay, and if I am just doing cylinder, sorry, not cone, cylinder, I'm sorry. So if I see this is like a cylinder in 2 dimension, and if I bring that one to the higher dimension, that cylinder will be something now rolled out like this. This is now like you are like folding, you are folding this cylinder, you are just completely now like unrolling it. This is rolled cylinder, you are unrolling this and making it to like a 6D, like now in the higher dimension you are making it like a plane. This is a plane and this is cylinder. So you are, for example, you are just you got that what visually I'm trying to say. For whatever the things in the lower dimension, uh yes, but what, see, compression means what? Don't now try to check with the PCA. I will just connect that to one. But what you are doing, whatever in these 2 dimension like circular things were here now. So now what I did, I just now cut here, and I like, this is something like you are having at your home some kind of a plate or some metal you bought for doing some construction. So metal you got it something like a fold one, like you got this folded metal and you bought it at home. You removed the things which binded it, you remove this, then it become unfolded, correct? It become unfold, so you got this kind of a plane. You got this one, you got this, how what I am saying? Okay, you are having some kind of a some kind of a water bottle, or some kind of a something like this is a glass. You at home we are having glass. I'm not good in the drawing, but this is okay. This is a glass you are having, okay? Or maybe I can draw something like this glass. This is the one glass. So I don't want to see this is like a glass, okay? But what I want to do, I want to cut that glass. This I want to cut this glass, okay? And I want to make a plane of the glass. This is now I cut. This is not now the circular. It is now the complete paper. Like paper means like complete flat now. Like I just now take out this, take out this. So now this paper is something like now. For example, this is one mark in the glass. The mark is still here. But now I did unfolded, like unfolding this one. You got this one, what I want to say? Murli sir. You got Murli sir? Okay. So what it want to say here, what I want to say here, so whatever the things in two dimension, like this is just example for you to visualize. So in two dimensions, these things was like a sphere or like a circle. Okay. Once I try to project that thing, the same circle, it was in two dimension. Once it is in two dimension, it is non-linear. But once I brought it to higher dimensions like f1 square, f2 square, and the same yeah, minus 2 f1 and f2, and here f2, and this is like your f1 f2 and your constant. Yes, yeah. So this is something like you are having some kind of point in the two dimension, and you are just unfolding it. You are having just unfolding that point here. So this glass, now you are tearing down. You are tearing down this glass completely. You just cut the glass now from here. You are having some plastic glass. You cut down, and now you make it like a complete plane. This is the glass. So now in two dimension it is showing circular relationship, but in six dimensions this is now complete plane. Okay, so what I want to say here, whatever the non-linear things are there in the two dimension or lower dimension, 2D is lower than 6D, 6D is a higher dimension, higher D means dimensions, so 6 dimensions is higher than 2 dimensions. So whatever is lower in the 2 dimensions, okay, you are now projecting into the higher dimensions, and you are making it as a plane, or a plane. What is that? Line in lower dimensions become plane, correct? In 2D you draw a line. In 2D what you do? In 2D you draw this line. In higher dimension what it looks like? It looks like, if I do the same thing, this line will be something like a plane which pass through the origin. So the same line is if I can show in the I think okay, but okay, so this same line, if you see in two coordinates, it's single line, but if I just tilt that, so it is something like a 3D. In 3D if I just see, it is something like a plane which passes through the origin like this. If I just see, it's a 3D. So something, if you try to project a line which is, if you try to project something which is in two dimension, which is having non-linear relationship, if you try to project that to higher dimension, it become linear. And what do you want in PCA? You want PCA things, all the points should be linear. You want, yes, so what you want in PCA, you want everything should be linear. If it is non-linear, what do you do? If it is non-linear, you project to the higher dimension, make it linear, do the PCA there, and come back. That's what the kernel PCA do. So this is the easiest thing. Okay, this is the easiest thing. Yes. So that's a point which we'll discuss tomorrow. But this is the idea about the issue number two. Like issue number two has the points which are in the points, if it is like a non-linear, the points in which are like a non-linear. So how to do the PCA on that? So what we do, we thought that okay, the point is non-linear in the lower dimension. Maybe for example we took f1 and f2, means these are the two variables, they are in two dimension, that's why f1 is 1, f2 is 1, means like d into so that's like a two dimension. So that two dimension, if you try to project to the higher dimension, that become linear, that's fine, that's become linear. Once that become linear, you do PCA there and then you will get the answer. So that is what we want to do, because see, PCA has what? PCA has a line. PCA has the PCA, what it will do in two dimension, it just draw the line. And the same thing if you see in the higher dimension, that will be a plane which pass through the origin, like the plane, or for example this is a flat TV, and it has something kind of this one, it passes through the origin. So this is like a three dimension, not good to show you in 3D like this, but this is like a has some kind of width. So this is three dimension things which passes through the origin. Okay, so if the line, if you try to draw, if you try to do the PCA in the higher dimension, that is something like instead of drawing the line, you have to draw like the plane and the line passing through the plane, something like this. And that you, if you want to just come back to the lower dimensions, that will be something like the line. So instead of doing PCA at 2D, you are doing PCA in 6D. Okay, instead of doing PCA in 2 dimension, you are doing PCA in 6 dimensions. Okay, so here what happened now, you are, so here what happened, so whatever your, yeah, no, there are different cases, like for example now I said you f1 f2, okay, f1 and f2, if there are like f1 f2 means circle, like only two variables, that's why f1 minus a whole square, and you do equal. If there are f1 f2 f3, like, or maybe like you can take f4, four values, like higher four values, four dimensions, here you took two dimensions. So what happened in this case, how you will project, because u value you need to calculate, correct? So here the u value, here you got the u value, correct? This u is equal to what? A square plus b square minus r square and all. And on this f1 f2 you calculated, correct? The feature map, because somebody has to be there who can like, for example, the small point on this location looks like this. If I am watching from here, if I am watching from the space, the point will be look like something like small dot, if I am watching from the space, correct? So there should be some person who has to say that this point is something like xy, or the latitude longitude, okay, latitude and longitude point. And you can see this point is very big in this if you are very near here. And if you are in the space, if you want to see the same point, I will send the latitude longitude to the space, and it will try to see the point from the space which is very small. So there should be some mapping, like if the point is bigger here, okay, means when you try to do Google Map car is coming into our house or into our city, and it try to get the same photos of your locations, cities, road and all corners and everything, correct? If Google Map things are coming, car is coming for mapping. Once you check that, once they update the Google Map, latest Google Map, if you see the map, then you will see that your things are like from space also they are visible, your lines are properly visible. So what they are doing, whatever they are watching now here, they are mapping with their another dimensions, like okay, from here it looks like this, then from top it also looks like this. So whatever the satellite images you are getting, they are mapping with your actual car, whatever car has captured, and then they are getting the final image. Okay, this is the best image, and this is the actual image of that house which is here. So in Europe and all, in America, you get maximum like a 3D maps, there is option of a 3D. Maybe India we have government restrictions, we can't show that many details in the 3D, but in Europe and all you can see that much detail, like how tall is the building, what is the how many floors are there in that building, and what is in front of the building. Though you from the satellite you can't see, but from the car they just maybe 6 months and 1 yearly, or maybe they will go with some frequency, that car come and go from your house and lane and all, and then it will see that from the street it will check that points, and they will map the points with the satellite image. They will say that satellite it looks like this, satellite shows this location like this, and your Google Map your car shows this one, and they map something. So there should be some kind of feature map function, like there should be some kind of feature map function or phi of x, which has to map your low dimension or two dimension things to the higher dimension to the 60. So that feature map, whatever feature map is there for your case, for example f1 f2 f3 f4 case, first parameter is 1. Okay, and now you are considering 3 dimensions as of now. Okay, so you are considering after the 4 you are considering 3 dimensions. So first is what, 1, feature map 1. Next is what, f1 f2 f, like I'm just thinking like taking it small. Okay, here afterwards what, f1 f2 f1 f3 and so on till f3 f4. Afterwards what, afterwards f1 f2 f3, then f1 f2 f4 and so on till that many values. But here what we are just considering the 3 dimensions, so we'll just take till here. Okay, I'm not going till another f1 f2 f3 f4 f5 like this. Okay, so here what, this is 1. Okay, so here you need to choose one of the values here. So what you have to do, out of these 4 you are choosing 1. So here you are choosing what, these are the two values. So here you are choosing out of these 4 values here, f1 f2 f2 f3 f3 f4 and then f1 f4 f1 f4. Out of these 4 values you are choosing to here 4 c2, because these 2 values 1 and 2, that's why you choose 2, 4 c2 1 2 3 4, 4 values. Okay, not dot. Okay, and here what you do, 4 c1, you choose one value because you want to 3 dimension f1 f2 f3, you don't want 4 f4, you don't want this, so I'm just choosing 1. Okay, so okay, here 1. So okay, 1, if I just do 4c1 is a 4, it's a 6, and here also 4. Okay, so here what happened, like your 4 dimensions f1 f2 f3 f4 is the 4 dimension things, and that 4 dimensions becoming 15. In the higher dimension it becomes 15. In earlier our example f1 and f2 we got 60, like 2D converted to 6D. Yeah, 2 to 6 map, they mapped 2 dimension to 6 dimensions, correct? So like this I can show this graph here. So here, so these 2 points are here, they mapped how the points looks. Okay, they mapped these 2 points to higher dimensions, like different, there are like a 5 will be like the 5 I showed you, f1 f2 and all. Okay, so there is like mapping function. Okay, that feature map, that map and the u value whatever you got, so it shows that phi transpose x, whatever feature map into your u vector should be like this is equal to 0. That shows the linear relationship. So whatever your 2D is now become 60 or 4. No, if here, no, if you see this, so now here see f1 f2 f3 f4, I need to choose 1. Okay, because here, so if I just do 1, I need one value from here. Okay, so I say that 4c1, which is like, you know that formula, n transpose upon r n c r, so r transpose of n minus r. Okay, like this. So here you will get like a 4 transpose upon 1 into 4 minus 1, this 3 transpose, so it's like 4, this value is 4, so that's why I put 4. The same way 4c2, because this f1 f2 I am getting na, this one f1 f2 f1 f2, because it's easy. Earlier we know that f1 I mentioned na, the for this two dimension to convert it to 6 dimension, f1 square f2 square, then f1 f2 then f1 and then f2, like this is 6 1 2 3 4 5 6. this 6 for the 6 dimensions, okay, from 2D to 6D. But now it is like higher dimensions, so I'm not interested in everything, so I'm just considering till 3D, 3 dimensions only. So f1 f2, so I'm just going f1 f2, and then here in from this I am taking 4c2, like this 1 2 3, and this 4, out of 4 I am taking 2, like because of f1 f2. And later on f1 f2 f3, from this, like they are also having 4, yeah, 4c3, and from this I am getting this here the 4 here. So if I do this addition, it's become 15. So 4D is now projected to 15D. Okay, 4D is now projected to 15D. Okay, but okay, but like now you understood that earlier thing. Now you understood, like whatever the lower dimension, whatever the 2D is here in the lower dimension, you are now projecting to the higher dimension. So lower dimension has a non-linear relationship, higher dimension has a linear relationship, because we know that phi transpose x into u is equal to 0. That shows a linear relationship. Okay, that shows your linear relationship. So what you want to show, here, that whatever 2D is projected to, for example 6D, or your earlier 3D, for example 3D is projected to like f1 f2 f3 f4, I just took that. So in that one I just consider only 3 dimensions, so I projected to 15D. Okay, so here the dimensions are increasing, correct? The dimensions are increasing. In lower dimension it is just 2, and now 4D to 15D. So in the lower dimension it is 4. Now a higher dimension is become 15. So we don't know also. Now I gave you the example. If there is like a 4D to 20D, there may be chances like you need something with more dimensions. For example, I showed 3 dimensions, but if I need something like higher dimensions, in that one I'm interested in higher dimensions. So 4D is mapped to the 15D, or 4D is mapped to the 90D, or 4D is mapped to the 25D. You don't know, the dimensions are increasing. So here the problem is, here the point is, dimensions are increasing, and we already know here dimensions, I will write here, dimensions are increasing from moving from low dimension to higher dimension. Okay, dimensions are increasing, and we know that when d is greater than n, just issue number 1 we solve it in the PCA. We just solve the equation when d is greater than n. We just know that d is greater than n. So in that case, so our issue 1, whatever the solution we have, whatever we think we derived now, okay, I hope it should come. Yes, yes, that things we will use into this kind of a scenario, when your lower dimension is projected to higher dimension to make it linear. Then you make it make it like a linear to the higher dimension by increasing the dimensions which are greater than your number of points. It's okay. In that case, you use your earlier solution from the okay, here it's come. I hope it should not be hanged, but yeah. So you use this. Okay, you use now these tricks when d is greater than, when your d is greater than n. You now use this algorithm, your issue 1 solution, to solve your issue 2. But still, like now whatever you projected, correct, you projected x, whatever x you projected in the lower dimension, I write whatever x you projected. X means your variable. Okay, that variable will be f1 f2 f3 f4, or f1 f2, or whatever. So I write x. So whatever these dimensions you projected in lower dimensions, by using some feature map you are projecting, and you are creating another f of x from that, which is like a higher dimension d. Okay, 2D is now converted to 6D in higher dimensions. Okay, and we already know how to handle by using this PCA. So what we are doing here, we are, see, in this equation, what you are doing, you are calculating k equal to x transpose x, correct? X transpose, oh sorry, x transpose x you are calculating, that is covariance matrix. but here there won't be a covariance matrix because it's now converted to phi of x in the higher dimension. So what you need to do, you need to calculate phi of x into transpose phi of x. So this is what you need to calculate, because earlier you calculated x is equal to x transpose x in the issue number 1 solution. Instead of that, now you calculate phi of x transpose phi of x. This is what we have to do in the higher dimensions. Like once you brought the lower dimensions thing to higher dimensions, now this become linear. Now this person is become richer in Africa. Now he can use the same money, because easy example, if some person is having $10,000 in America, he cannot purchase a house, but he can come to USA, and he can come to Africa, and with that money he can fulfill his dream. He can fulfill his dream means he can do his PCA. So the same person in America can't purchase the house, but in Africa he can go and purchase the house and claim that, oh, I fulfilled my dream, I did all these things, I bought my own house. He can stay there, that's all, or he can do whatever things. Okay, the same way, the point is 2D. He can't 2D is like a non-linear relationship in the lower dimensions. In America he can't purchase the house. He just come to the Africa, he just map these points to the higher dimensions. We moved from 2 dimensions to 6 dimensions. Okay, and in 6 dimensions now he can do PCA there, because he is like a rich there, he is like having a linear relationship there, so he can do PCA on there. And now he is happy that, okay, I have done my PCA, I have differentiated my points from like I have written, I draw some best line there. Maybe the best line won't be there, it's a best plane, which the plane which has a line passing through that, so that will be the line, so going to the plane passing to the origin. So that is the best thing he can draw in the 3 dimension or higher dimensions, whatever he has. But there he should not use x is equal to x transpose x, because that's what we do in the issue 1 calculation. We calculated k is what, covariance matrix, and that is equal to x transpose x, but that is 2 dimensions, which we don't want to do anything in the 2 dimensions because it's non-linear. Okay, then do phi of x transpose into phi of x. So this we can do this same operation there, just by changing, instead of k equal to phi transpose k x transpose x, we can do this one. But there are some other challenges will come, that we'll see tomorrow. Maybe tomorrow we'll finish this PCA, because there are only 2 lectures remaining, 2.4 and 2.5. We'll finish that part tomorrow. That is what the kernel PCA algorithm. But the theme of kernel PCA is this one. Whatever like kernel PCA or anything, whenever the kernel points will come, now kernel points comes means there is a problem with the point in their lower dimension. The lower dimension has some issue, not showing linear relationship. Okay, then make it to the higher dimension, make it higher dimension linear relationship, bring the linear relationship there, make it linear there, do whatever calculations you want as per your algorithm, that's all, and bring it back to the lower dimension. But it's not needed, but you can go with the higher dimension that time, that's all. But we'll see tomorrow the remaining things. Any questions till now? Yep, so you can maybe yeah, yes, so just go through the video. Hmm. Correct, 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 correct. Uh, that you mean to say they are catching this Murray, this one, the ships which carry drugs in America, like this, you want to say? That is not the that is like a real time satellite imaging, and they are like capturing GPS and all. But GPS, that is something, then they have to use radar and all, but that is different point. The radar thing, they will detect the vehicle and they will track the vehicle, how the vehicle is moving, or submarine is there, submarine is moving from this, they will use the sonar and or there to get that. But this, yeah, but here the PCA, like here in this, okay, okay. So what I want to say there is something like you maybe if you have seen this, the car which generally they have some kind of a cars, okay, and the car has some lidar sensor here, okay, okay, and they will just simply, their work is just maybe yearly or 6 months, they will just go through the lanes, from the all the lanes, okay, they will go through the lanes and see is there any changes happening or not, like if there is some construction going or not. Yes, now also they do. So you, they also sometimes say that on that day we are visiting on this street and all. So the sometime if you see in America, people will do jokes and they will try to, when the car, they see the car, they will try to show that they are like falling down on the on the surface or something like comedy things they will show. So yes, yeah. So there will be some kind of feature map, like whatever the points you are now, like you are now seeing these points. For example, this is one building at the corner, okay, and you are now seeing this building. And what happened? Like now you consider there is one building, but now there is some construction going on. So these points, they know about this point, okay, and in the in because this is lidar sensors capture this complete data, okay. So what happened now, once you have the data, the car will come to their station back, and they take out this hard disk and all, they try to get the data. Now the satellite will also capture the data on the same time, like the satellite is here and it try to get the same house from the top view, like the how the looks like. So house looks like this for the satellite, for example, and for maybe little bit small or something, but not having enough information, and the car will have more informations from this end. Yeah. So what they will do, then they will map this, they will map these cars data points with the satellite data points, like 2D to higher dimensions and all, and they will create one final image of the building, like if there is some front side and back side of the building, and they will construct the final. Yes, you. Yes, 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 yes. Because this, see, you are not uploading your house photo. Somebody is coming in your village, and so that's what they do. They are mapping. They are having some. Yes, yes, yeah. They are having some mapping function phi of x, which map your lower dimension things to higher dimensions. Means like whatever image they are seeing, they see, and then satellite image they will map together, because satellite is going all over the world, okay. So they have like maybe we have geostationary satellite, so it is just getting complete India's photos and videos and all. So that image and your own image, if Google has their own satellite towards India, to on India, so they will get their image and your inside car image, they will map together, because car don't know whether he is in Tamil Nadu, and that time satellite is in Hyderabad, so he has to map Tamil Nadu only. So there should be some map functions with the latitude, longitude, directions and all. So that map to your 2D images to higher dimension, then finally create some 3D graph of your building, and once you go in the Google Earth, you can see your area location in the 3D. So this way they map your lower dimension to higher dimension. So same way in our PCA, two dimension is like I just gave the example there, but in PCA same way, two dimension is like non-linear and you are mapping to the higher dimension, and a higher dimension is showing now linear, and once you are in linear, that's what you want, and you do the PCA there, and you are the happiest guy in there, like that's all. Yes. So we'll stop now here. I think this session goes very